pleasure to welcome all of you on my own behalf. My name is PK Das, and I'm actually from the Indian Institute of Science, and I'm currently the chair of the Science Education Panel of the Academy. And on behalf of the Academy, that we are very glad that you are here in this Science Education Panel lecture and discussion symposium. Science Education Panel aims to reach out to all people who are associated with education in this country. For example, we have programs, summer research fellowship, lecture workshop, and summer school for students of different categories. We have programs for teachers through this kind of lecture plus discussion, which is generally are held at the time of the annual meeting and half-yearly meeting of the Academy. The aim of the Science Education Panel is to spread education and keep everybody updated about what is happening in different branches of science today. And in that endeavor, we run these various programs, and I guess some of you probably were associated with lecture workshops, organizing lecture workshops in your respective institutions, or you have participated in refresher courses. Now, sometimes we choose different subjects, and this time we have chosen three subjects: physics, mathematics, and computer science, but basically engineering, okay, to highlight some of the recent advances, some of the old knowledge, everything together. And we have three eminent speakers this afternoon. I'm not going to give a long introduction to them because you can do Google search these days and find everything about anybody that you want. But more importantly, I'm not going to actually take away their time. So they are going to talk about their subjects, but at the same time, there will be discussion after the lecture, and you can ask them questions. And so that when you go back, yeah, I hope that you get excited about some new directions in that subject, the subject where you belong to. You may be a mathematician, you may be a physicist, you may be an engineering scientist. But whatever you are, and all the speakers have chosen topics that are relevant today. Okay? And so therefore they're all updated on what is going on. They're very eminent and they're going to talk to you. And so please pay attention, ask them questions, and I'll actually continue to be here. I'll be also a listener like you, but I have to also conduct the whole proceedings, so that's what I'll do. So with that, those few words, let me again welcome you on my own behalf and on behalf of the Academy to this afternoon program, which I hope you enjoy and you take something back home from this. Thank you very much.
I'm going to talk to you about astronomy and how it can be done from ground and space. And my name is Anupam Srivaran, and I am heading the Indian Institute of Astrophysics. And so through this talk, what I would like to convey to you is how the field of astronomy and astrophysics are. You need the mic. Yeah. How this field of astronomy and astrophysics are being pursued, though astronomy and astrophysics astronomy for that matter is one of the ancient sciences. So how is it relevant now, and how are we progressing our understanding of the universe these years, and how technology is playing a major role in this. Okay, so that is the overall crux of the matter. And also I think everyone for that matter gets excited about astronomy and space in general. So what are the kinds of research that are carried out, and what are the upcoming major projects where India is participating? So that also I'll be touching upon. Yeah, so generally you would see pretty pictures, right? The one which I've shown here. So pretty pictures are what you see from any kind of popular articles in astronomy from space. A new picture taken by James Webb Telescope or a Hubble Space Telescope or something like that I hope you are aware of the, I mean, heard the Hubble Space Telescope, etc. Right? So these are making a lot of news in the social media, the WhatsApp messages you get, and also the prints, etc. So one thing before I start telling you about astronomical pictures is that these are all false color images. So sometimes you will see the sky in a wavelength which your eye cannot see, right? But you have to depict in a way where you can understand how that is seen, right? So you will depict in a color which your eye can see, but that's not the true color, right? So that, but what you can believe is the intensity distribution, like how, where it is intense, where it is faint, where it is bright, that is correct. But the color which is shown is always is not correct, not true. It is actually the color which the visualization purpose you give the color. So sometimes the nebula will be in one color in one somebody's presentation, it could be in a different color in somebody else's presentation. But the intensity, the way in which where it is dark, yeah, so that is one thing you keep in mind. Like you have a radio picture of a radio galaxy, and you could also see it in this kind of a intensity. Intensity is true, but the color you attribute is because you cannot, the eye cannot see the wavelength in which that measurement has taken place. So you have to give it a different color. So intensity is correct. So all astronomy pictures will have false color images. So whenever there's a disclaimer, it will be there's a false color image. So all that we are able to measure is the intensity at a particular wavelength. And that wavelength, some of the wavelengths are visible to our eyes, but some wavelengths are not. Ultraviolet, X-ray, radio, infrared, you cannot see. We cannot see it from our eyes. But if you want to see an infrared picture, James Webb Telescope sees only in infrared. So how do you tell someone that this is what the telescope is seeing? So you depict it in a color which is weak eye can see. Okay, so they all the most of the astronomical images are false color images. So that you should, as a teacher, you should keep in mind that. Okay. So, the ground based astronomy from 1609 onwards, we know that Galileo pointed the telescope towards the sky. That's what we believe. And maybe somebody has done it accidentally before or after, I mean, before that as well. But then, as per records, Galileo is the first one who has pointed the telescope to the sky. And he saw the mountains and craters on the moon. Since then, astronomers have been using the telescopes to point out to any celestial object to study what it is. Now we have extended it from the optical to various wavelengths, and thousands of ground based telescopes operate right across the world. That is the bread and butter of any astronomer, astrophysicist, because that is the way only you. Astronomy is a subject where things are far away. You cannot go and touch it, and right now you can, but I'll add to it later. But you can't do the experiment in terms of other physics. You can actually cut it, chop it, dissolve it, whatever you can do, pound it, do anything under the microscope or whatever you can do it. But you cannot do it in astronomy. So what is available to the night sky, or the sky is your laboratory, and you have to collect the photons, electromagnetic waves which are emitted, and you detect it, and use the detection to infer what you have collected. So these are the different steps involved in the in astronomy. So if I write it, I'm just deviating from the normal talk I would give, because I think you are teachers, so it will be very important for you to express it in terms of anything you see. You have to break it down into its components. So it's like you have, let's say, the light. So you have anything, you have galaxy, galaxies, clusters, or planets, you know. So anything is there. So what are you getting is the light. Light means it is equivalent to a electromagnetic wave. Now, this is what is the classical astronomy, but right now we are also changing. If you are aware of the discoveries which were announced a couple of weeks ago, which were on identifying neutrinos in our galaxy, map of the neutrino of the galaxy, that's the particle detection. And second is the detection of gravitational waves. So right now we can see the universe in terms of electromagnetic waves, Also gravitational waves now, which is actually added up very recently, and other high energy particles also you can, okay, apart from neutrinos. So this is the way in which, so the thing is, this is everywhere, omnipresent. Now you have to collect it, detect it, analyze it, and infer. So these are different steps one needs to go through. In any physics experiments for that matter, you would have these kind of steps. But in astronomy in particular, because why do you want to collect it? Because if you look at the sky, you can only see some stars, right? But if you use a telescope, the aperture, what you can collect the photons is proportional to the area of the collecting surface. Your eye has a fixed area. So if you want to increase, you can increase the collecting area of a telescope. So smaller the telescope, the collecting area is small. The bigger the collecting area, the number of photons you collect is more. So you have to collect. And then you have to bring it to a focus, just like your eye does. Using a camera, you detect it. Again, how efficiently you collect and how efficiently you detect will depend upon what you can analyze and infer. Just to give an example, we know the solar system has planets, right? Now, 30 years back, we did not know that the other such sun-like stars had planets as well. There was hypothesis that outside sun-like stars will also have planets like our sun. Now, how do you know they exist or not? You don't know, right? So the only way to do, how do you detect it? First of all, the question is how do you detect it, and whether are you able to detect it, and if so, how do you actually say that I have detected a planet? So this was a question 30 years ago. Okay, people did detect it. Now this has been known that most of the sun-like stars have planets, right? So that is the development we know in the last 30 years, right? Are you aware of you are aware of this, right? So now how did we do that? Yeah. So what was the change? So it was there all along, is that we could not detect it. So what is exactly we achieved is the smartness in the way it is collected, smartness in the way detected. So what do you mean by smartness in the collection, and what do you mean by smartness in the detection? So the thing is, it's just a very rough example. It's a very raw example, I could say. But if you say sun-earth system, you say earth is going around the sun. Do you say sun is going around the earth? No. Why? It's a two-body system. Take it as a two-body system. One body is going around the big one. Just this is going around each other. Now, what does it effectively go around? It will go around the center of mass. You understand the center of mass concept, right? The center of mass will be somewhere between the line connecting the two. So if these were two equal bodies, the center of mass would be somewhere near the center of it. Now, if it have unequal bodies, where will be the center of mass? Closer to the massive body. Now, if you consider Earth Sun system where Earth is extremely small compared to the Sun, where will be the center of mass? It will be inside the Sun, but not at the center of the Sun. It will be somewhere very close to here, right? So, what will happen to the Sun? Movement of the Sun because of the presence of the planets. Can you imagine? You assume that there are two particles which are going around, right? So everything it will not see the other particle, whatever it is. It will see the center of mass. Each body will go around the center of mass. This body will go on the center of mass. That will go on to the center of mass. Now the center of mass is within that body. How will it behave? It'll do a small wobble, right? It will not be like an orbit, but it will do a wobble. This is the wobble you have to detect. One has to detect. So it's extremely precise measurement. The wobbles which are, so sun is also not is going around the center of mass. Earth is going around the sun. Earth is actually going around the center of mass of the system, and sun is also going around that center of mass. And any star which has got a planet will have such motion because the center of mass is not coinciding with the center of that object. This is a very simple physics, extremely simple physics. Now, how do you take that wobble? How does it wobble? It'll go around that center of mass, right? So, in your line of sight, so this is very astrophysics would, this is exactly what it wanted to convey, that though I talk about large telescopes and it's very fancy and very engineeringly, technically it is very complex, etc., the physics involved is very simple, and astronomy uses basic physics and actually makes it to astrophysics, and these are the basic things you need to know. Like, I want to know the movement of a particular object. How do I know? I have to deconvolve into two components. One is the velocity towards you, one is the velocity in the plane of the sky. So if it is going around something like this, there will be a component of the velocity which is towards the observer. So an object is going away from like this, so you can actually deconvolve this thing into this, right? This is the total velocity, this is the velocity in the sky, and this is the v radial. Radial is the one which is the component which is coming towards you. Now, this is simple Doppler measurement. The velocity which is the signal comes to you is Doppler blue shifted, which is going away from you is Doppler red shifted. The light which is emitted by the star will be blue shifted when it comes towards you and red shifted goes away from you. But then that change is extremely small. So the more you collect the data, you will get more signal. The better you can detect it without noise, you will get better signal. So the signal is what we are looking at. So this requires both technology to make sure that you have minimum noise. So I'll give you one example of detecting exoplanet. The other point is, this is when this thing is moving and going away. This is the velocity measurement, nothing but a Doppler shift. You have to measure the Doppler shift accurately. Second is, like I'm seeing something like a star, like this picture. You have the star and the planet is going around like this, right? So when the small planet is going in front, have you seen Venus transit? Venus going around like the sun, right? So there'll be small dots, like blobs on it. How much light can it block? Very little. So if a planet is going around the star, periodically you will get a light blocking. How much? Maybe 1%, maybe 0.1%. So typically it is about 0.1%. So you have to detect the variation in 0.1% in the light. So your detection accuracy should be extremely good, like 1,000 counts you get, the variation is of 1. Your precision has to be better than that. So precision measurements, the detection and collection precision are required there. So astronomy, these ground-based telescopes are basically the workhorses, but the way you design the instrument to make sure that you collect maximum data, you make sure that your noise is minimal to get accuracy of one photon in 1,000 photon, accuracy should be there, right? Then only you can see the small dip. So if this goes, if your count is going like this, let's say you have a 1,000 count, when the planet comes here and travels up to here, you'll have a small dip, and then it goes up. So this dip is of 1 photon in 1,000. So it is very carefully done, very painstakingly carefully done. So astronomy, though it is ancient, requires extremely precise measurements for making any advance these days, because whatever you could do is already done, but we have so many unknowns still. Like only the last 30 years we know we could detect planets around stars like our own sun. Second, gravitational waves, which is detected a few years back. Now we know that there is a gravitational wave background as well, so I'm not going to touch on that, but I'll tell you what you do from space and ground together. But I'm saying that in general, Astrophysics requires instruments which are extremely precise. Okay, measurements have to be precise. And there are, you also have space telescopes as well as ground telescopes, right? If you have know that big telescopes, which are the biggest telescopes in the world, there are two 10-meter telescopes in the Mauna Kea Mountains. And this telescope, before going to the previous one, I should also say that this one is a 2-meter telescope. 2-meter would mean the aperture. This aperture collecting area is 2-meter, primary mirror is 2-meter. And that 2-meter is that telescope which is located in the Himalayas, which is at 4,500 meters above sea level. Why? And this is the night sky you see there. This is a beautiful night sky, and the pattern, anybody knows what pattern that is? Any idea what that is? What is this pattern which you see in the sky? Mhm. No, it is just the sky. It is a galaxy, Milky Way. Yeah, this is the Milky Way galaxy, which you can. This is the obviously processed image, but you can see it naked eye in Hanle. If you go to places with dark skies, which are actually not there, not many now, and these dark skies actually you can see with naked eye. The patch, the Milky Way patch is clearly seen. And this place is Hanle is about 8 hours, 200 kilometers from Leh, which is in Ladakh. And this is at an altitude of 4,500 meters above sea level, which is about half the height of the Everest. Very cold, high altitude desert. We've been operating this telescope for the last 20 years. But if you want to collect the data, going there will be very tedious, right? So you don't go there. You have to go to our observatory or our campus in Hosakote. We have been remotely operating it, but our engineers live there. But this place now, because the development is taking place everywhere, right now, I don't see any place where you can go and see a night sky in and around Bangalore. But this can happen to this in another 2 decades. So we are working with the local union territory and the locals, and they are also very keen to protect the area. And so the 23 kilometers around this observatory is now notified as the first dark sky reserve of the country, where light pollution will be controlled, and also sustainable development, and no large structures can come, and the villagers have to be will be the custodians of this. There are 7 villages, and those villagers will be the custodians of this. So we will put the rest of the things in place now. So unless and until we protect even the younger generation, maybe many of you would have seen some good night sky when you were young. I used to grow up in a place where I've been fascinated by night sky during blackouts, or there was used to be something called power cuts, where you can clearly see the night sky. I don't think any of the younger generation can even imagine how the sky would be because they have not seen it. So this is what we are trying to do, at least in this area. Apart from, of course, astronomy and astrophysics and other things. So similarly, this is another. So you can have telescope on the ground. So you say that okay, light pollution is there. Why do you want to put it on the ground? Why don't you send it in space? Right? Telescopes are in the space. Why do you want ground telescopes and why do you want space telescopes? If you have problems in the ground, you have cloudy skies. Cloud doesn't clear anywhere, so you can't see anything. Why don't you send it in space? Right? That's a question. Or you say the space is some problem is there, you put it on ground. Or do you need both? So that's another question. So the question is that the ground-based telescopes are generally placed in isolated elevated locations. That's what I told you, right? You'll have observatories which are far away from the city, in a hillock, top of a hill or something like that, so that you can have clear skies, etc. And the scientists and engineers are turning to space for new frontiers for advanced telescopes. But this began in 1960s when balloons, and then now the idea is to get a good view and without cloud coverage, etc. But it's got its own problems and advantages. Advantages is it's above the Earth's surface, Earth's atmosphere. Atmosphere doesn't cause any problem with it. No light pollution, no cloud cover, no rain. So you can operate it anytime you want. but throughout you can operate you want. But the problem is you have to lift it up and put it in orbit. Like the instrument, if I'm saying that I'm putting this computer in the rocket, it should survive the shakes and the bakes of it, right? It can get heated up, it can get shaken, and the parts can come off. So even if you change this to one place, the wires will fall out, right? It cannot happen. So you cannot, if it has to be foolproof, and it has to work in all conditions outside the atmosphere as well. So testing is becomes too tedious, and it also is very expensive because the our atmosphere protects everything. And you should be aware of it. High energy radiation is not coming down. Our particles are not coming down. But if you put something above, you are exposed to all the high energy radiation out there. So your system should work. So this is the telescope in Nainital. Have you anybody gone to Nainital? No. Okay. So this is an Aryabhatta Institute in Nainital. So this is actually the top one is an observatory called Devastal. This is a 3.6 meter Devastal observatory which is started operating the last in 2016 onwards. And this is a telescope in Kavalur. So it's in the Vainabapu Observatory Kavalur. This is operated by us. So there are few institutions in the country who are well versed in telescopes and also setting up observatories and uh, continuing their science, use the data from their science, etc. Now, giving a brief history of our institute, which is the Indian Institute of Astrophysics. So this is a simple history. In 1786, it was formed in Madras. It's called the Observatory of Madras in Chennai. Then it moved to Nungambakam, and then it moved to Kodaikanal in 1899. So anybody have gone to Kodaikanal? Okay. So the observatory in Kodaikanal, anybody has walked in? Okay. So this observatory is ours, and in fact that was established in 1899. And from then onwards, we have been capturing the pictures of the sun continuously. So 1904 onwards, we have been observing the sun continuously. And this long data, long 100 years data is available for public for analysis from our website. It's readily downloadable. So you could have imagined for 100 years, more than 100 years, the technology would have changed, right? The way you capture images, you have to store it, you have to preserve it. Anything you photograph, you put it in an album and keep it, you see for fungus in few years. So you have to make sure that it is stored well, protected well, and that is done. And recently we have digitized the entire thing and calibrated images, so you can actually readily do science with it. No mismatch between those observed in 1910 to 1930 to 1960, etc., etc. So sun has got a 11-year cycle. You probably would have known. Sometimes people will say the sun is active, and sometimes people say the sun is not active, right? So the sun has got a 11-year cycle. You please read up about it. There's a lot of material is available. So solar cycle is 11-year cycle, and this cycle sometimes is good, and that means a lot of sun is very active, which means sun is just spitting out a lot of plasma into the interstellar space, in the planetary space. So what is the impact of it? You have heard you will definitely get WhatsApp messages saying that you have to switch off your phone. There's be some flare coming up and charge particles, and most of them are actually fake messages. So please ignore it. Don't even please do not forward it to any more people, because it's already forwarded by somebody to you. So this is normally fake, but of course sun does spit out plasma because of magnetic fields. So what is this 11-year cycle? Is the magnetic activity. So if you want to study 11-year cycle of a magnetic activity, you need to have multiple 11 cycles to actually study it, right? This cycle has happened. Next cycle, what happened? So previous cycle, what happened? So that itself gives you 33 years. So we have 100 years of data. So you can actually study the sun cycle. Okay? So after that, we started moving to we became Indian Institute of Astrophysics. The same observatory became an autonomous body under the name IAA, and now we have completed another 50 years under it. So this observatory, and since then we have developed a lot of observatories and spread out wavelengths, etc., etc. So where and all we have So if anybody wanting going anywhere, please do visit our observatories. They have visitor center and also places. So we have a few observatories down south, and then three of them in the uh, Leh region, and we have two space telescopes. One is up there for 8 years now, so almost 8 years. The next one, Aditya L1, is going to go in August. So this one is going to go in August. This will be 1.5 million kilometers towards the sun. And we also participate in other major telescope projects. So we are basically, dirtied our hands in making telescopes and building instruments and carrying out research. Now there are some of the pictures. So this is, you can see that one is the coronagraph, which will fly to the 1.5 million kilometers. This is our Hanle Observatory. This is our facility in Hosakote. Um, and this is also a place where we remotely operate the telescope. This is a Gauribidanur Observatory, which is for radio wavelength. This is an optical. These two are telescopes. This is the Astrosat, where this telescope be integrated, and it is up in space. This telescope actually goes over Bangalore once in 90 minutes. So this is any telescope, any kind of you launch a payload and a rocket, any mission, it is there, but it has to go around the Earth at any. It cannot stay stationary there, right? So it will go at some velocity around the Earth. It has to make an orbit. So this makes a. This is at 650 kilometers. It's called, we call it as near Earth orbits. Like Hubble is at about same 600 kilometers. The International Space Station, for that matter, will be at 350 kilometers because you can reach it. Further away, it is difficult to reach. So this is at 650. And this will go once, 90-minute orbit. Every 90 minutes, it will pass through Bangalore. This has been doing this for the last almost 8 years. So it's going at very large speed. So your instruments up there should be able to cope up with all this. At the same time, collect data and beam it down. So it is a bit complicated. So if you want to send a telescope up there, it is a good idea, but then you have to struggle through it. So I just want to skip a few slides. So maybe this one is worthy. So why do you want space? This is the electromagnetic spectrum, where this is the optical window. So atmosphere does not allow all the, it is good for the life on Earth for that matter, because if because of the atmosphere the Earth has, life has been able to survive. Why? Because the layer stops all the high energy radiation and protects the life forms. And so this block for shorter wavelengths is done by the atmosphere. Now, because of this, if you put a detector down, you can't see anything because that's going to be absorbed by the atmosphere. Any radiation coming from here, you can't even collect it because somewhere this atmosphere will be absorbing it. That doesn't mean that anything out there is not emitting in that wavelength. Like for the sun is emitting in ultraviolet, but we don't detect it, right? We can't reach it because otherwise we'll have all sorts of problems. So that is stopping. Sun is also emitting in X-rays, but it will not reach the Earth. But if you want to study the sun emitting in those wavelengths, where will you put your instrument? Above the atmosphere. So there is a necessity for wavelengths if you want to study like X-ray or UV. This is a necessity. In the optical range, you can collect it on the ground. But if you go to infrared, where if you want to study an exoplanet where where the life form exists there or not, like the molecules which are biosignatures. These are molecules which will have the transitions in, they are in the infrared transitions, right? Because the transition energy levels are very, very small. So the transition actually happens in infrared because the energy is very small, that the split between the energy bands. If you want to detect them, this is the infrared, this is the infrared band. Now, we cannot detect it on the ground because the water absorbs them. The water vapor in the atmosphere absorbs them. So, like our Hanle Observatory is at a high altitude, it's a desert. So, you look for deserts which have very little water vapor. So, then you can probably beat these. But after that, in the more than 10 micron, this is completely blocked. Again, for this, you have to go up. So JWST is up there, which is observing in that wavelength, which is actually in space. So this is the radio wavelengths where you can actually, yeah. So the radio wavelengths you have the full visibility. So even if you want to do, you need to figure out which wavelength is accessible from ground. And for those wavelengths, you may have a space or ground together, but there are wavelengths which you have to depend only on space payloads. So development of space payloads becomes a necessity if you want to do this kind of wavelengths. And there are lots of payloads which I've studied, and Hubble Space Telescope. These are some of the images. This is the Compton gamma rays. This works in X-rays. This is the Hubble Space Telescope. This is the infrared. So this kind of major space telescopes by the US and the Europe actually helped us to map the universe in various wavelengths. It told us, so what is that we are trying to study? If an object is able to emit in X-rays, what is the physical process which is giving rise to the emission of a photon? So again, that is only physics. Because if you want to study like for how many people are sitting inside this room, how do you do that? You don't have any light. Okay? So if you want to put a detector somewhere up in space and see whether people are there in this room, how do you do that? I think some people have gone to sleep. I just want to see whether anybody has any response. If you want to study that, trace that people are sitting in this room, because it is also a military requirement. No, people do see how where the military people are moving. So you remember sometime back there used to be. Uh, let us people speak up, then I'll come to the answer. I don't want to see that. What are the ideas? Radar, infrared, something else? Thermal, thermal imaging. Anything else? What is that? SAR, synthetic aperture. It's radar. Synthetic aperture radar is what you're talking about. So thermal is one thing possible. Thermal radar is a different way of looking at it, because you look at the reflected beam back and then you analyze it. But thermal is because thermal, there are two different properties you're looking at. So idea is that either you're devising a technique, right? You want to trace something, you have to devise a technique. The technique will depend on the property of the material, whether it is emitting or in reflectance. In the case of thermal, this is the property you're looking at is the emission property of the people, right? So everybody's body has a particular temperature, and you're trying to map the thermal. That's why it's thermal called, right? Your temperature is you're trying. So that thermal is fine, but what is that? What is the technically what do you use it? It's an infrared. It comes in the infrared bandwidth. Then you have to have an infrared detector, right? So what you have to understand the emission process, emission mechanism or reflectant mechanism is again physics. Right? If I want to say a body is, will you be able to use an X-ray detection to detect people? No. There is a property by which the, the human body, for that matter, or humans emit in a certain temperature. Because we have a temperature, that temperature peaks in a particular velocity. So you have to choose a detection mechanism that detects that wavelength. So it is the question you're trying to answer, kind of a thing. In the case of radar, it is actually the reflectivity. Okay, so you can you I don't know whether it is temperature dependent, but that has to be understood. You don't need a temperature variation; you won't be able to see. But the reflectance variation, you can see it. So the point is, if an object is emitting a particular photon, I detect it. So what? Then it comes to the analysis. One analysis that you are making a light curve. You're making a detection of time series. I'm collecting it, T1, T2, 3, T4, etc. for a few hours. And then I'll plot my count as a function of time. Then I see this, then I infer it.
I see this first. So this is the analysis part. So first you analyze it. You have to have the error bars and all that coming in. Okay, so once you step into physics, then it becomes quite complicated. Then you say that okay, this division is there, but then is it statistically significant? So all those things will come in, but you will get some analysis. Then you say, what does it mean? So then you have inference. Here you need to produce a lot of theoretical models. Because if this has to happen, if this is the case, this you get. Is there any other way in which you can get this curve? Because this is sacrosanct. This is you have measured. This you cannot dispute this. Any other measurement should bring it this. But then what you infer from here? How do you infer? There you have to do models. So there can be millions of models. This is like philosophy. You can say anything. But then somewhere it has to be proved practically by measuring. So you can bring in any kind of models, but the models have to have a prediction, it has to match this. So their inference will be depending on many models. So in astrophysics, theory plays a very important role. Theoretical models are extremely important, without which I cannot even say I made all that painstakingly. I made the telescope, I have detector, put everything and I measured. I don't know what it is. So without models, you cannot complete the story. So in physics also, I think we need to have models for that matter. So in astrophysics also, we have models, then only it gets completed. So similarly, these telescopes observe all these pretty pictures. Pretty pictures are an output, but that is not the science beginning of science. There you need to figure out why is it emitting like this? What is the physical mechanism there? That is inferred from models. It could be electrons getting accelerated, or a mass falling down, accelerating materials or particles, or something else, heated up material, cooling down. So various things. It's a physical phenomena, but except that, if you talk about temperatures here, you talk about 30 degrees, 40 degrees maximum, or to 0, or minimum you can go to -10, but their temperatures will be 10,000, 20,000, or temperatures could be few Kelvin, etc. So the range is very large. So that is the difference in astrophysics. So it also lets you look back in time, where you can say that how the universe formed. So this is some of the things which the wavelengths also allow, as well as the large telescopes also allow. Now I just want to have a quick time check. I want to skip a lot of slides because I just went off track to explain very fundamental things on the board. Let me just skip through. Yeah, so this one thing which I can explain, that this is the Earth. When you have to put the telescopes on the space or in your space missions, there are different types of orbits it can take. This is the low Earth orbit. This is why Astrosat 650 kilometers. HSD is here. You also can have sun synchronous orbit, which is actually going pole to pole. So depending upon what you want to put, this is basically 90 degrees. So here is a very interesting concept. This is you can consider it mainly two body system, but there is a third body out here as well, Moon. But if in the two body system, as I said, there will be a place where the particle put here will actually be the gravitational force here is such that this particle can neither go here nor here, because the attraction becomes it becomes cancels out. The force of attraction over here and force of attraction over here is on opposite sides, so the test particle out here is stationary. So that is called the Lagrange point. Similar Lagrange points are there in the orbit over here. So this is the L1 point, where this is 1.5 million kilometers, this is also 1.5 million kilometers, L1 and L2. Now L2, if you look at James Webb Telescope, or in last week, I don't know whether if you're watching the news, there's another telescope called Euclid, which is also to study the space, went up in orbit. All are going to L2, away from the Earth, away from the Sun. But the telescope, which is Aditya L1, is going here, which is 1.5 million kilometers towards the Sun. So if Aditya L1, which is launched next month, end of next month, in fact next week, Chandrayaan 3 will go up, and to the moon. This is the moon mission, and this is the mission to the sun, and this will be placed here in an orbit like this. And this is actually, there's nothing out there. It's a null point. It's no object there. This point will move along with Earth when it orbits. So the spacecraft will orbit an inner circle around the sun. It will be able to have an unrestricted view of the sun, and it will also trace the particles in the inner area because Earth is further away from it. So what happens to the space particles within that thing will also be studied by that. So, and the last part is data. It's important that the missions and the data collected by the telescopes are available, made available. So these are different sites which are from the HST, but there's a similar site for the AstroSat data also. So telescopes data also are there, like what I said about Kodaikanal data from of the sun. Like 30 years back, because the technology was not available, websites were not there, data was very scanty. People used to collect data, lock it up in their drawers, will not give. Difficult to do science because you can't get data. Without data, you can't do anything. So data was not available. But now the data is flooded. You don't have time to look at the data because data is so much. You don't have, humanly not possible to look at the data. So we are in the other two extremes. One, there was nothing. Now there is too many. But the data is available. You want to look at all the data, then you need to have tools to look at all the data. But you still can choose your science cases to access the data and do it. But the advantage is that data democratization has taken place. Everybody can access data. Anybody can access data. Anybody can have laptop. Anybody can have internet. You can download the data. Similarly, tools are available free of cost. Previously, if you want to have an analyzing tool, you have to pay for it, right? You have to buy the license. But now most of them are open source. You don't have to buy. You don't have to buy licenses. Of course, there are still some licenses, but you still can manage with it. So the research can be done by anybody, as long as you know the fundamentals. So I want to stop here by saying that, I have a few slides on TMT where India is participating, I'll just skip, but my message is that many things will happen. Technology will change drastically. Scenarios will change drastically. Fundamental is the most important foundation you can, if you put, you can even, demolish your first floor, construct another first floor. Something you can do, but if your foundation is not strong, you cannot do anything. So put all your efforts in foundation. Anything can change, doesn't matter. You can make a new coat of paint, you can change your window, you can change a lintel, you can change your roof, doesn't matter. But put your foundation properly, just like in the house. Foundations are good. Any change, it's going to change drastically. Scenarios will change drastically. You'll be able to absorb it and also convey to people. But you cannot do it if your foundation is not strong. So please put a good foundation for your students, for yourself. That will take you through all these kinds of changes. But without it, it's very difficult. But I'll become irrelevant in another few years if you don't keep understanding and updating myself. Updation is one, you have to be current. You need to have your foundation strong, then there's no problem. You can always break it down the problem to the minimum level and understand it and take it forward. Just a few slides on. Yeah. So these are the basic telescopes. Yeah, so the big telescopes which are coming up in the next 15 years or so. So I said the collecting area has to be increased. You can keep increasing this collecting area. What is this? This is a mirror. So normally telescope, what happens is you have a light coming from infinity, just falls inside here. I'll just make a small one. Light falls from here, from infinity. The objects are at infinity. It comes to your focus here. You can put your detector here, but you can't hang things here because it's in front of the mirror. So generally you put another mirror here, bring the light down, and put it here. This is how generally telescope works. This is the primary mirror, this is the secondary mirror, and this is your camera. Okay. So this is, as I said, is a 2-meter telescope we have. The aperture is 2 meter. Now, if I want to make the collecting area bigger and bigger and bigger, how far can I go? It's a single mirror. You can't go beyond. Right now, the technology doesn't allow you to go beyond 8 meter because it breaks and it's too risky. You have to polish it and all that. So, is that the limit? You cannot create a constructed telescope beyond 8 meter. No. If things become that kind of a technology doesn't work, you have to have something called disruptive thinking, right? So that kind of an effort, what people have done is now don't do this. So instead of a single aperture like this, you make it into smaller segments. So it's called a segmented mirror telescope. So you can make a segmented mirror of hexagonal type, and then put another one here. This segmented mirror you actually create and fill it up. So segmented mirror can be of the order of 1.4 meter. So this can go up to very large scales. So if you look at JWST, James Webb Telescope, this has got 18 mirrors. Overall it's 6.5 meter. But the problem is, if you have the small pieces of the mirror, how the heck is it going to work as a single mirror with accuracy? That is where the support is required. Active support and precision. Precision engineering and precision support. So if you place it like this, it cannot stay like this, it has to move, right? Then the gravity will act. Different things. You have to actively support it. Again, like this, you have to actively support this. The technology is known for the last 2 decades. If you look at Keck telescopes, they work like that. So James Webb Telescope, which is up in the space for the last year or so, more than a year and a half, is the first segmented telescope in space. So it is very crazy that you put it up there and balance it there. So it is a crazy one, but that's what it is. Now we are going to do a mirror with the 492 segments. So this is the one, and India is participating. And India is actually putting up, these are the segments, hexagonal segments. And this is the support assembly. India is going to, of the 492, India will do about 115 to 150 of them. And 492, the segment support assembly, this has been made by Larsen and Toubro, L&T, for the entire telescope. We have to make 1,000 odd pieces. Edge sensors are to sense the edges between the mirrors because the mirror segments cannot come together. This is done by Indian industry. And actuators to push it up, move up and down, is also by Indian industry. So this is supposed to come in another 10 years' time, but India is at 10% level with Indian contribution, and Indian Institute of Astrophysics is the lead institute for this project, and Indian industries are participating in it. So there are other projects like LIGO, which is announced now, and so many more such bigger experiments are also coming to astronomy. So it has got a good future, and you should be aware of these things because there'll be a lot more news and things like that progress in that direction, and many people will be involved in these projects in the future. Yeah, I stop here. Thank you.
I have one question that when I collect the data from some stars or something else, so how can I confirm that it is coming from that stars or that point only? If there are two stars are very close to each other, and how can I find it out from the data? Because it is only radio is coming. So
yeah, it's electromagnetic.
Coming from that particular one, what I am searching for.
Yeah. So I'll just give a simple example. You have two lights here. Two lights here. Both the lights, the photons are coming to your eyes, right? But are you able to differentiate which photon is coming from which light? But you can see how much the two light sources, right? So similarly, as I mentioned, what is your eye doing? It is focusing the photons coming from various directions. That focus will tell you which part of your retina has got photons from which source. That is why this is bright, right? More photons are arriving from here to in the retina. You have an image, and that so a part of this image where this light is coming will be brighter. That is why you are correlating that with this particular light. Similarly, when you get this data from the parallel beams coming from the up in the sky, you get an image here. You get an image here. So this image will have many things.
If you have two different sources.
It'll be separated, right? If as long as if you have another light which is near to it, it is to do with the resolution. If your two sources are so close that you cannot resolve them, then it will be merged.
How does the telescope can resolve this?
Yeah, telescope
this?
that's what we have a profile.
Yeah.
This profile can separate how these two sources can be resolved. If in principle you'll get so many stars in the sky.
But which one is for the which stars it is coming?
You will know the angular resolution of the sky, you can make it. Similarly with it's extremely same as the terrestrial. Like if you can see, if you are high resolution, you can see each leaf in a tree which you have imaged.
If there is some noise or some other
No, that is to do with the signal.
radiations come from some other sources, then
No, you have to disentangle your things. Three things you're talking about. One is spatial resolution. Right? One that you understood.
yeah.
Two things are nearby, you should be able to separate. Two, second is signal strength. No, temporal you're not even reached. Signal strength. And three is the noise. Right? So if I do this here, resolution is this is your. If you are able to do this, you can resolve these two. If they are wide apart, this is the PSF of the point spread function, right? What the point source it gets spread because of the optical elements out there. So these are two different things you can definitely resolve. The point is how big they are. These are the photons which comes, right? So if this is your noise, your signal is only this much, you can't. The signal has to be this much, you can. That is why you need to have this area under the curve is the same. This is the number of photons it is emitted per that particular time, unit time. Now, if you want to have a better detection, you can do this. If this is worse. Right? Because area under the curve is the same. The number of photons it's emitted by the source is the same. The spread is what matters. If it has to be coming above the noise, either the noise has to be less or the signal has to be peaked. So you have to bring down the noise, or you have to make sure that this width is reduced so that it becomes something like this. So that is when your optics have to be pretty good, device has to be pretty good. And the location of the telescope. If it is in a good observatory, you will get this. Otherwise, you will get this. The entire thing will be washed away. Yeah. So three things you said. Temporal is different. Temporal is per second, how much is the variation?
Ground-based telescope, is it country specific or region specific? And what is the difference between astrosax and ground-based telescope? Because in the other part of the world there will be darkness. One country is night and daytime. How do you integrate data? So what is the difference?
Correct. So I have not talked about calibration. So there's something which comes under calibration. So the source is independent of where you observe from America or India or Japan or anything. And the measurements you make, absolute measurements, should be same irrespective of where you have made it from. Right? Japan or, except that it will have a time tag. Right? So you have to correct for the atmosphere around it, above you. For example, rising sun, can you look at the rising sun? Have you seen the rising sun? Have you looked at the sun at noon? Are you able to see it? No. It's the same sun, no. Why is that? Huh? The sun became faded when it rose and became brighter when it noon? No. So what has happened?
Radiative power is
Coming further intensity.
I'm the same.
it's perpendicular.
Correct. Why? The sun is same now. What happened to sun? Sun was red. Now up in the noon it becomes yellow. No, you are perpendicular to the sun anyway. So all the there's no definition of perpendicularity, right? Because it's just the eye and the sun. Eye and the sun. Of course, there's a trick there. The thing is the following. I just want to connect it to the observations. That is why I'm bringing that analogy. Yeah. So the point is, let's say I just give this is the person standing here. This is the sky. Let me see. Just it's a pictorial, but don't take it in literal way. So this is sun here, and setting sun. Okay, these two are enough. Now this is the distance you get the atmosphere. It is where is it passing through? Passing through the atmosphere. So there will be scattering. But here the length at which the light has to pass through the atmosphere is the atmosphere, okay, not the sun. The atmosphere is much more. So what happens to the light when it passes through the atmosphere? Rayleigh scattering. So Rayleigh scattering is why we see the sky is blue. But this scattering happens to what happens to the source you get? There is a finite amount of scattering which happens. Along with scattering, there is also dimming. Right? So the dimming is one. That is why the intensity of the sun, rising sun, intensity of the noon sun are different. There's one more thing which is different. The rising sun is red. This one is yellow. What has happened to it? Correct. So the blue light you have lost. So the more the scattering, the more blue light is lost. Right? So because of the atmosphere, one is red. We call it reddening. Because some things are reddened. Now this happens to all the sources you observe. The amount of reddening will change from here to Nainital to anywhere you do it, south, anywhere, in US, Japan, anytime you observe, in the night also. So you have to correct for these two on a nightly basis. You observe from the ground. So even if it is okay, the object is right now we have daytime, US has nighttime. So people do put across the globe telescopes, all these places, so you can actually continuously observe across the longitudes. So you can have a 24-hour coverage because we have only 12-hour coverage or less than that. Put on the telescope on the opposite side, you can have a full coverage. But timely coverage, you have time. So these corrections need to be done. Once you do the corrections, calibration is done, then it doesn't matter. It doesn't matter what instrument you have used, it doesn't matter where you have observed. As long as you have the time tag. So these corrections are okay.
Feel free to stop me at any time and ask questions. And I want to have several. I want the entire talk to be understood. Okay? I hope you won't get lost, and I don't want you to get lost. I want to take all of you along through the talk. However, I will also have several takeaways. Okay. So the first takeaway is the following: is that by a takeaway I mean something that a small bit that you forget the rest of the talk. You can just take this, and that's something you have learned, and so something you can say, okay, it was worthwhile just for this reason. Okay. So it's the name of a person. It's the name of a mathematician, Jun Ha. Although it's H-U-H, it's a Korean name. It's Jun Ha. Okay? And have you heard of of course, there is no Nobel Prize in mathematics. There are Nobel Prizes in chemistry, physics, medicine, and other things. But there is no Nobel Prize in mathematics. Of course, these days there is something called an Abel Prize, which is sort of a Nobel Prize in mathematics. But instead, what the mathematics has is a Fields medal. it works very differently from Nobel Prizes. It's not awarded every year. It's awarded every 4 years only, once in every 4 years. But not in, typically to 2 or 4 mathematicians. Okay, so minimum 2, maximum 4. Okay, awarded every 4 years, and it's awarded during a very important conference called the International Congress of Mathematicians. Okay, ICM, International Congress of Mathematicians, which, like the Olympics, happens every 4 years. And it happened in 2022, and June Han was one of the 4 who was awarded the Fields Medal. So, by the way, to win the Fields Medal, you must be under 40 years old. If you're beyond 40, then you don't get to win. Okay, so it's a very different kind of prize, unlike the Nobel Prize, which is more like a career prize, right? Of course, it's also given for one spectacular achievement. Okay, and so that is the first takeaway. So you could Google or type June Han into your internet search and look up. In addition to being an excellent mathematician, Fields medalist level of that level, he's also an excellent expositor. So his papers are very lucidly written, and usually mathematicians, that level of mathematics is not easy for many people to follow. But this is an exception. Many of us can follow lots of things that he has written. Okay? So that's the first takeaway. Okay. Now coming to the talk itself. So the Fields Medal citation for Ha, among other things, so I'm skipping over certain things, mentions the following 2 items, and those are the 2 items I'm going to concentrate. Okay, so of course we can go over all the items very quickly, and possibly we'll lose. So rather I'll concentrate on one particular item in which the other will also make an appearance, so that we can all understand and get some appreciation. Okay, so this is will be this word Lorentzian polynomials. Of course, the name is the Lorentz transformation, the same. The Lorentz is the same Lorentz. So the theory of Lorentzian polynomials, for developing the theory of Lorentzian polynomials, is one of the things he was awarded it for, and I'm going to give you a definition of the Lorentzian polynomial. Yeah, that's another takeaway. And the strong Mason conjecture. So, just to make sure, do we all understand what is meant by a conjecture? Right? When somebody, like Fermat's last theorem, although it's called a theorem, it was a famous conjecture. Right? So, is a statement which we cannot prove or disprove. Right? Somebody says this is true, and sometimes it's so. Either you must establish that this is correct, or say no, this is not correct. Here is the example. Right? So a conjecture is one where we are unable to decide about its truth value, whether it's true or false. And mathematics, the business of mathematics is mostly through, conjectures. There are many open. So these are the things many mathematicians concentrate their they focus on. So this strong Mason conjecture, I will explain what this is. This is very simple to understand. Okay? So I'm going to explain to this. Everybody can understand. It's at high school level. It was open since 1972. So it was made around the year 1972, about 50 years ago, and it has been open. Usually, of course, mathematics has conjectures, you might have heard of the gold bar conjecture or the Riemann hypothesis. The gold bar conjecture is maybe 300 years old. And twin prime conjecture. So these are very old. There are many conjectures that are 100 years old, but this one is a very simple-minded conjecture, and it has been open for it was open for 50 years about, and it has been recently solved, and that is one of the it was shown to be true, and that is one of its achievements. Then I am going to tell you what that conjecture is. The Mason is the name of a mathematician. So this, sorry, I should have been. So the strong is, there's something called the Mason conjecture, and there is a strong version of the Mason conjecture, and the Mason is the name of a mathematician. Okay, so this is, so it was made by Mason, and that's why it's called the Mason conjecture. Okay, so okay. The other takeaway that I want you to have is something called a matroid. Have you heard of this term? No. Okay. It is a term that many mathematicians have also not maybe heard, but this is a definition that is worth. It's something that is needs to be better known. Okay? So I'm going to define a matroid and tell you what the Mason conjecture is, and tell you a little bit about how the proof of that goes, and in that the Lorentzian polynomial will make an appearance. So this is the structure of the problem. Okay? So let us begin. Before that, two more references. So I'm not sure if you are aware of this. Does this word make sense to you? No. Okay. Okay. Yes, and some are saying yes, and some are saying no. Just note this down. Okay. And if you type it into your Google, internet search, so this is archive where scientists put up their papers these days before publication. Right? Preprints. Exactly. So it's a preprint server. It's spelled this way, and if you type this in, you will get the paper that I'll be talking about. This one is not by Ha. Okay? This one is not by Ha, but a different set of 4 mathematicians. And the proof that I'm going to talk about is not actually due to Ha, but them, because that's more accessible, a little more accessible. But anyway, that's a reference. The paper is at college level mathematics. It's something that your master's students, if you have, can do a project. Okay, and finally, one last reference. Okay, so if you want to follow more about this talk, there's a video recording on YouTube of this talk that I gave at IMSC, which is a little more technical. So I'm just going to give you the reference for that, rather than give you the YouTube link. Okay, I tried this out on my laptop and it worked. It's the first. If you type this in, my name, matroid, IMSC, that's the institute I'm from, and lecture. If you type that into your internet search, that's the first title you get. So it's a video recording of a talk that I gave. It's a little more technical than the one I'm going to give now, but similar. Okay? So much for that. Okay, now let's start doing the math. Okay, so I want to define what a matroid is. So this is an abstract definition, as we call it in mathematics. Okay? So what does it have? So there is an underlying set S. It consists of a set S, which let's take it to be a finite set. Okay? And you can even take it to be that set to be, because it's a finite set, you can just take it to be 1, 2, 3, or 2n. The first n positive integers. Okay? And it has a collection of subsets. I is a collection of subsets. this is not the collection of all subsets of S. It's a certain it's a collection of certain subsets. Okay, these subsets will be called independent. That's the terminology. Okay, and these independent subsets must follow certain axioms. Must be subject to certain axioms. Only then do we call this collection S together with I a matroid. Okay, so what is a matroid? It's an underlying set, finite set 1 through n, along with a collection of subsets, which must follow certain axioms. I'm going to write down the axioms in a minute. Okay? But before writing down, as we should do in all mathematics courses, but we don't often, we should give examples. Okay, so let me, even before writing down the definition, let me give you an example of a matroid, okay, of a collection of an underlying set and collection of independent subsets. So, can I use this board or is it? I can. So, suppose I have a matrix like this. So, let me write a matrix 1, 0, 0, 2, 0, 0. So, matrices all of us understand, right? So, just think of these are vectors in R3. If you wish. Okay, 1, 0, 0 is ijk, you can think of. This times I, this times k, j, this times k. So, this is j, this is I, and so 0, 0, 0, 1, 0, 0, 0, 1. And so there are 6 columns. So I'm going to number the columns. So here, in this example, the set S consists of 6 elements, namely 1, 2, 3, 4, 5, 6. Okay, so that's this underlying set. And when do I call a subset independent? So, suppose I take the subset 1 and 2. Okay. For that to be independent, I take those two vectors. If they are linearly independent in R3 as vectors, then I call them independent. If not, then they are not independent. Okay? So, by convention, if I take the empty subset, that's considered independent. Okay? It's just a very basic normalization. Okay, so let's do this. So the empty set is independent. What other sets are independent? If I take the first vector, is it linearly independent? Yes. So let's write down all the subsets that are. So 1, 2, 3. How about 4? 4 is not independent because it's 0. Okay, 4 is not independent. So 5 by itself is independent, no problem. 6 by itself is independent. Okay. How about 1 and 2? They are not independent. So 1 and 2 I cannot write. Right? How about 1 and 3? Independent. Very good. Now you know how to do it, right? Let's do it. 1, 3. How about 1, 4? See, 4 itself is linearly dependent. So 1, 4 cannot be. So if you have something that is dependent, meaning not independent, then anything containing that will also be dependent. Okay? In other words, if something is independent, any subset of it must also be independent. That is one of the axioms. So let me start writing the axioms here. There are 3 axioms. One is that the empty set should be independent, should belong to this. Second, if something is independent, any subset is also independent. Okay? So I'll write it like this. It looks a little strange in notation. What it means is if something is independent, then any subset is also independent. So I'll write I contained in J, and J belongs to this collection, implies I belongs to this collection. I hope you are comfortable with that those symbols. Okay? That's another axiom. And there is this last axiom, which is perhaps the most interesting. Let's come to that. But let's complete this example. 1, 3 is okay. How about 1, 4? 1, 4 is not okay. 1, 5. 1, 5 because of this 1, it's linearly. 1, 6. 1 and 6. They are independent. Okay, 1 and how about 2? Now 2 with 3. Yes. 2 with 4 is not good because 4 by itself is not good. So anything with 4 I can ignore. 2 with 5. Good. 2 with 6. Independent. Very good. Okay, now how much? 3 with 4 is not good. 3 with 5. Good. 3 with 6. 3 with 6 is also good. Okay. 4 not good with anything. 5 with 6 is good. By good I mean independent. Okay. I've already started using slide. So now let's come to 3 subsets. So tell me that 1, 2, 3, okay? 1, 2 itself is dependent. So 1, 2, 3 is not. Okay. So let's see. Anything with 4 is not good. So 1, 2, 3, 1, 3, 1, 3, 5 is also not good. 1, 3, 6. Very good. 1, 3, 6. Okay. And a few more. 2, 3, 6 is also good. Okay. 1, 5, 6, very good. 3, 5, 6, 2, 5, 6. Okay, sorry, I'll write it here. 2, 5, 6. 3, 5, 6. Okay, and so on. But you get the idea. Let me see if I have 1, 3, 6. 1, 5, 6. 2, 3, 6, 2, 5, 6. 3, 5, 6. I think we have everything. But never mind. You know how to do this, right? So let me write down the final axiom now, which is motivated by this. So if I have some, let's say, a large number of independent vectors, say 5. Of course, you cannot have this in R3, but you could have a matrix. If the vectors were in R5 or R10, you could have clearly 5 vectors which are linearly independent, right? And if you have another subset which is say 3 linearly independent vectors, then out of these, because these 3 vectors span a 3-dimensional space and these 5 vectors span a 5-dimensional space, there must be definitely something in these 5 which I can add to this and still keep it independent. That is, if I have a smaller independent set and a bigger independent set, by the smaller and bigger I mean in terms of size. If I have fewer elements in this independent set and more elements in this independent set, then there is definitely one element from the bigger independent set that I can pull out and add to this smaller set and still keep this independent. Okay? This is a property which is true for vectors of this kind, and that we abstract out and say this property must hold. So what we are trying to do, so let me write down the property and make a few comments. So sorry, my board work is not good. So here, this is the final axiom. That is, if I and j are independent subsets, and you understand by this notation the number of elements in I, right? That's the notation. If it is less than j, right? So if I is a smaller independent set than j, then there exists some element j in j. Okay? There must exist, in this case, some column, which I can add to such that I can add I to that. So j not in I. By that I mean in j but not in I, such that when I add j to I, that still is independent. Okay, so this property is true, which is true for vectors of this kind. I abstract out and try to study all objects with that property. Okay, you might say this looks crazy. Why would you want to do this? But this is the business of mathematics. We want to, so mathematics consists of trying to understand what is it that is driving. If given something like this, maybe these are all the properties that you need. That's all that is driving. Okay. So anyway, be that as it may. So this is a metroid is a set, underlying set, along with a collection of independent set which satisfies these axioms. This is the definition of this completes the definition of a metroid. And here is an example. Okay. Let me give you one more example before we go on. Okay. And that comes from, here is an example from linear algebra, which is a basic subject in mathematics. The other sort of very basic subject in mathematics is graph theory, which doesn't require much background to understand at all. Okay, so let me give you an example from graph theory.
Did we miss out 2, 3, 5 here or?
2, 3, 5. 2, 3, 5 is not they are dependent because 5 is 2 plus 3.
But according to this rule, 2, 3, 5 should come here.
Why should it come?
Because you said this independent thing, you can independent element you can add to it, but it's still a given.
But if I have so no. See, there must exist some j. So what is your I at j? 2, 3. You can take 2, 3 to be your I. You choose your j.
J is actually 5. So if you say 2, 3, 6 is coming to 2, 3, 5.
No, let's see. Let's do this slowly. So 2, 3 is I. Now for this hypothesis to be satisfied, you have to choose a j. So, and j, there is only 3 element subsets. So one of these is j. So you can choose your j. Tell me what I should choose my j.
Okay, 2, 3, 6.
2, 3, 6. Then that says there exists out of these 3, there is something that you can choose that you can put it into this and it's independent, namely 6. It's not saying that if I choose any element of j that's not in I, I'm not saying any, you can't say there is, you can, am I making it clear? Yeah. So, for example, no matter which one I choose here, right, if 2, 3 is my I, and j, capital J, is one of these 5, then 6 is there. I can take that 6 in all of, each of them 6 is there, and that is the element that will satisfy this. This 6 is not in 2, 3, and I can add that 6 to I, this, such that it is still in. Thank you for that question. Yeah. So this there exists. It is not that for every, you cannot choose j that you, this j is not in your hands. All I'm saying is, I will find you a j. That's all I'm saying. Is this okay? Any other questions?
Metroid is an offshoot of matrix or Metroid is an offshoot of matrix or?
Definitely it is motivated by this from linear algebra and therefore matrices like this. But the point is, having abstracted this out, it turns out that these properties come from other sources as well. For example, I'll tell you one from graph theory, but these are not the only sources. So this often happens in mathematics, that you make a certain definition and then lots of different things come into it, and there are unsuspected applications of what you have been studying. Okay. for example, non-Euclidean geometry, which I believe is useful in astrophysics. It is the underlying geometry of general relativity is not a Euclidean geometry, if I'm mouthing the words correctly. But the non-Euclidean geometry was discovered, used by mathematicians of the 19th century. Okay? And much before it became physically relevant due to Einstein's relativity. Okay, let's do the graph theory example. It's also very illuminating. So definitely, to answer your question, the word matroid seems to be motivated from the word matrix. It was defined in the 1930s, so it's not quite 100 years old. Okay? But definitely, mathematicians is still not well known even among the mathematical community. Definitely deserves to be better. Okay, so let's do another example of a matroid. So I take a graph. By graph, it just means there are finite sets of points, which are called vertices, and some edges between. Okay? So let me draw an example. So there are 4 vertices, and this is my graph. Okay? I'm not going to name the vertices. You can call them 1, 2, 3, 4, 5. Okay? I will, however, name the edges. A, B, C, D are the edges of the square, and E is this diagonal. Okay? Now, I will say, so the S will be, the underlying set is the set of edges, in this case A, B, C, D, E. Okay? And I have to tell you what I works for this. And the I that I will tell you will satisfy these properties, these axioms. So, I must choose subsets of edges. I choose any subset such that they don't form a cycle. So, for example, if I choose all the 5, that will not work because this is a cycle. Right? Cycle means a tour where I start from one, and go around and come back to the same. Right? So if there is a cycle among my choice, that is not work. Okay? So let us now given that, tell me what I is. I is, of course, empty is always there. Okay? Can I choose each single edge? Yes. If I choose A, there is no cycle. If I choose B, there is no cycle. I can choose all the single ones. Okay? Okay, and I will not bore you by writing down all but I'm going to question you. How many 2-element subsets are there? There are 5 elements. So how many 2-element subsets are there? How do you do this calculation? 5C2, 5 choose 2, which is 5 into 4 divided by 2, 10. So all the 10, so there will be 10 subsets of cardinality 2, meaning of size 2, all of them. Okay? And how many will there be of size 3? First, all subsets. N choose, NC 3. Oh, sorry, 5C3. 5C3, which is how much? 5C3 is the same as 5C2, which is also 10. Okay? But can I choose all of them? No. For example, if I choose AED, that's not going to work, right? So how many can I choose? I mean, I can't choose AED, so AED is not good. BCE is not good. The rest of them are wrong, correct? So let me just write 8 subsets of cardinality 3. And anything of cardinality 4? If I take something of cardinality 4?
I see 4.
No, okay, yeah, there are 5 of them, correct. That's the total number of subsets. But any subset of cardinality 4 among these, if you choose 4 edges, there will be a cycle on this. So you cannot choose, right? So this is it. Okay, so that's our matroid. This is this underlying set, and this is the collection of subsets. Okay, is this clear? Okay. Now I'm going to come to the next step. I'm going to tell you what Mason conjecture is. It's a very simple statement. Now, the statement is the following: if you have a matroid, we have given 2 examples, but here is where the power of the mathematics comes in. These are just 2 examples that we have constructed, but there could be ever so many sources of these examples which satisfy these axioms. Okay? Now, here is the statement. So let's write down I0, I1, I2, etc. Where I sub k, this means it's by definition the number of independent subsets of cardinality or size k. Okay. So, for example, let's do this in this example. So I0, what is I0? So I'll write down I0, I1, I2, I3, I4, I5, etc. But you tell me what these numbers are. What is I0? 5. So what is I0 therefore? It is the number of independent subsets of cardinality. So I0 is the number of independent subsets of cardinality 0, and there is 1, only phi. So this is 1. What is I1? 5. What is I2? 10. What is I3? 8. 8. What is I4? 0. And then the rest is. Okay? So let me first tell you what the Mason conjecture is before telling you the strong Mason conjecture. It's very simple. It says you write these numbers, you take any one number, look at the 2 numbers beside it. It says the square of this number is always bigger than or equal to the product of these 2 numbers. So here is Mason's conjecture. Let me write it. It says ik square is always bigger than or equal to ik minus 1 into I. It's as simple as that. I mean, you might say, what is there? I mean, it's obvious in this case. But the point is, there are so many matroids you can construct, right? They're coming from all over the place. And for each one of them, you have to either show that this is true or show me a witness, show me an example where this is not of a matroid, where this is not. Okay. So this turned out to be this looks like a very simple thing, right? You take a matroid of one of these kinds, write down these numbers, and the point is, people wrote down lots of examples and found that this is always true, but there is no way of proving it. But you have to establish your proof, and that's what has happened here. That's part of the recent advances in combinatorics, is that this has now been proved. Only the last less than 10 years. Okay. So is this clear now? What Mason's conjecture is? Now let me tell you the strong Mason's conjecture, which is a slight variation of this. Okay. And it just says the following. So we are saying that this number here is bigger than or equal to this number. Okay. Instead of writing this, I'm going to make this number slightly larger. Okay, I'm going to make this number slightly larger and then claim that yet still this number is bigger than or equal to that slightly bigger. So this is Mason, and let me write now strong Mason. Of course, now that we have proved this, this only has a historical interest. Okay? So the strong Mason says the following: ik square. So here I'll let n be the cardinality of S. So I'm going to write n here. 1 by. So I'm going to multiply this by a number which is slightly larger than 1. Okay? And that number, for example, I'll write this. So it's a number slightly larger than 1. I multiply this by that number, and then it's still larger. So I can also multiply it by this number, and it's still larger. So this is a stronger version of the conjugation. Not only is this bigger than or equal to this, the product of these two, but you take this product and also multiply it by these two factors, which are slightly bigger than 1, and therefore this will become much larger, and ik square still beats. Okay, that's the step. Now, before I start talking about the idea of the proof of this and how the idea of Lorentzian polynomial comes into the proof, let me rewrite this conjecture a little bit. So you must have guessed, even in our examples, the numbers, the binomial coefficients n choose k played a role, right? When we said, for example, what are all the subsets of cardinality k from a n subset? It is nck, or I'll write this as, you may be more used to this notation, but it's the same, okay? nck or n choose. So this actually, it's a small high school exercise that you can rewrite this. This is, if you rewrite this like, you can modify these IKs by dividing them by the total. See, this is the number of independent subsets. This is the set of all k subsets. So this is the fraction that is independent. This is the total number of k subsets. This is the k subsets that are independent. So this fraction, square of that, is bigger than or equal to the fractions for these. So this is just another way of rewriting that inequality, and so this or this is called the strongest. Yes, sure. Questions about that? Yeah.
The Mason conjecture.
Yeah.
You have to define k.
No, for any k. So this is sorry. Good. Let's write it. I meant it, but did not write it. For all k. That's no matter which k you choose.
But if you go to 0, then it works.
But it works. 0 square is bigger. This square is bigger than equal to this is
that takes care of it.
yes. It is bigger than or equal to. So, for example, if what it means is if this is 0, then this has got to be 0. So the first time, what it means is you hit there is 8, there is 0. This has to be 0 because this square is 0, and if this is anything positive, then it's going to work with violently. So if this is 0, then this is 0. Yeah, good question. Yes. This is this is for all k, and n is the cardinal. Yes. Any other questions? So again, I repeat, in any example that you write down, it looks like a very, trivial thing. What is that? Okay, let's even try this. What that would mean is, I would divide 1 by 1, divide 5 by 5, divide 10 by 10, divide 8 by 10. I'm dividing by the binomial coefficients. And even then, the square of the middle one is bigger than or equal to the product of these two. So for example, here it's 1. 1 square is bigger than 1 times 4 by 5. 1 is bigger than or equal to 4 by 5. Okay? Right? Now, let me quickly tell you what the proof involves. Okay? So the proof involves a beautiful idea of this Lorentzian polynomials. And so what is the so what you do is the following. This is again a very standard technique in mathematics. To study a sequence of numbers, you don't study them bit by bit. You make it into a single object by doing what is called a generating function. In physics, sometimes partition function or something like this is called, right? Or you can, in this case, you can just make it into a polynomial. So, for example, I'll write this as I0. I'll choose two variables. Let me call them x and y. So, x to the 0, y to the n. N is the number of. Okay? So, let me just decorate it by I0, x0, y to the n. I1, x1, y to the n minus 1, and so on. Plus ik, x to the k, y to the n minus k, and so on. After n, all of them are 0. Beyond n, there are no subsets. Right? So, plus so on. So, you will get a polynomial. Okay? This polynomial has non-negative integer coefficients, right? Because these are the numbers that I get, I0, I1, and k, are all non-negative integers by definition. Meaning they are cardinalities. Ik was the number of independent subsets. So that's a non-negative number. It might be 0, but it's either 0, 1, 2 or something. It's a non-negative number. Okay? So now you study this polynomial as a function. So you can think of this polynomial as a function on, say, this is, you choose this x and y coordinates and look at the plane. Right? And it's a polynomial with non-negative coefficients, and so you can study it as a function on this part of the plane, for example. Okay. Now, the point is this: this polynomial has the property that it's what is called log concave. So this is something that we can understand. So let me explain what this means very briefly. Okay. So you understand convex functions and concave functions, right? So if a function is like this, right, in one variable, this is a what you call, maybe you call it concave downwards, right? And something like this is concave upwards. In mathematics, it's standard to call this convex. Concave upwards is called convex. This is called concave, just by convention. Okay? So when we say concave without specifying upward or downward, it means concave downward. Right? Now, what does log concave mean? It means that a function is, if f, you take a function and note that this is a positive function because these coefficients are all non-negative. Therefore, if I evaluate it at any point on this here, x and y are positive, it's going to give me a positive value. So I can take logarithm. Okay? So I can take logarithm. This should be concave. So log concave means logarithm of f is log concave, means log f is concave. In other words, can you just remember from calculus So in terms of the second derivative, what does it mean for a function to be concave? See, for first derivative tells you whether it's increasing or decreasing. Second derivative tells you whether it is concave upwards or concave downwards. So if the second derivative is negative, that's what, in other words, the second derivative should be negative. Okay. Now that's if you have in one variable. Now if this is a function in two variables, and we want to talk more generally about functions in several variables, then there is an analog of the second derivative. Okay? So it is called the Hessian. What you do is, see, second derivative is what? You take d square f by dx square. Instead of one variable here, we have several variables. So what you do is, you take partial derivatives with respect to all combinations, okay, and arrange it in a matrix. Okay? So you have if I have n variables, then I will have del square f by del xi, del xj, and there will be n square of them. Of course, except if they commute, very good. So that, but for the moment, let me not bother that they commute and put them in a matrix. Right? So first coefficient, 1 coefficient will be del square f by del x1 square, and so on. So what I get if since you said they commute, is that it's a symmetric matrix. Okay? And for a symmetric matrix, you can talk about, just like, this is a very important concept in undergraduate mathematics. There is a notion of positive and negative. It's called negative definite. Which means, okay, and for lack of time, let me not explain. So there is just believe me that there is a notion of negative. And log concavity means that this matrix is negative definite. That is, if I take, let me write log here, because it is meant for the log of that function. So I take this matrix, this n by n matrix should be negative definite. Then I call it log concave. Okay? And the theorem is that this polynomial that you have is not only log concave, it is log concave, but it's slightly more. It is what is called Lorentzian. That is, not only is it log concave, I'm skipping over some technical detail, but let's not worry about that, because intuitively that doesn't make any difference. If I take partial derivatives, so if I have a function, see, look at this is a polynomial. I can take partial derivatives with respect to x and y. So I can take two partials with respect to 2x and three partials with respect to y. And every time I take a partial derivative, the degree of that polynomial comes down by 1. Okay? So what it means is that if I take partial derivatives, they should continue to be log concave. So this polynomial has the property that not only is it log concave, that is, this matrix is negative definite, but all its partial derivatives, no matter how you take partial derivatives, they will also have that property. Okay? And this is the theorem that's the proof. And the important point I want to make here is, this is really a new definition. So the importance is that not just this f is log concave, this polynomial, but all its derivatives are also log concave. This is something that mathematicians took some time to understand. And in definitions, good definitions are as important as good theorems in mathematics. And Lorentzian means precisely this. Not just is log concave, but all its derivatives are log concave. Okay? And once you hit upon that definition, then the proofs, see, the importance of a good definition is the following. See, you know some theorem to be true, but you are having difficulty proving it because you are not, there is no pathway to proving it. But if you make just the right definition, if you make it too strong, then there are examples which fall, you're not going to catch all examples. If you make it too weak, then you're not going to be able to prove what you want. So it has to be just right. So this Lorentzian definition, for which it's cited, Joppa is cited, is one of the important nice, beautiful definitions that mathematicians have discovered in the last 10 years. Okay? So maybe I'll stop.
Okay, so time for a few questions. And our next speaker is here, so we have to
Law content is strongly law content. It's not a positive definiteness for all the derivatives. No, that's something.
The negative definiteness for all the derivatives and a little more. It's so it suppose I didn't define it. It should be indecomposable. That is, yeah, you should not be able to see. So x square plus y square. If I write a polynomial like that, it is one polynomial in x, and so you should not be able to break it up. X square plus xy plus y square. So that's an indecomposable. So it should be indecomposable, and it should be log con. All derivatives should be log con. That is the definition of strongly log con. Or Lorentz, which is the same as Lorentz. Sorry, did I make sense?
No.
Okay, thanks.
So any physical possible network, any physical, for example.
Of networks, of course, these graph theory and linear algebra are all over the place, but there are other important networks as well. Combinatorics is full of networks. Lots of things in combinatorics, and therefore in all of mathematics, can be captured by this language of networks. Yes, they are a very good definition.
Okay, so good afternoon. I think we will now descend from the rarefied heights of Mason conjectures and combinatorial mathematics. It was a fascinating presentation, down to the more pedestrian world of data science. And I think most of you would have seen, especially if you have been reading the popular media and the newspapers and the social channels, that data science today is viewed as essentially the buzzword of choice, especially in the software industry. And everybody thinks that this is going to be the answer to all the problems in the world, no matter what it is, including the Bangalore roads, which for we know is a grand challenge in computer science, which can never be solved. And the assumption is that this is going to be the magic wand with which you address all problems. But what I'll try to do in the course of this talk is to try to give you a slightly more sober and nuanced view of the field, and actually point out that data science can also be dangerous. Certainly, it can be a force multiplier, but on the flip side, if it is used in an indiscriminate manner, it can not only lead to incorrect results, but also potentially dangerous results. So at the end of the talk, I'll try to make the case that data science should not be used as the first tool that you have. It should be used as the tool of last resort. And it should not be used as a substitute for domain knowledge, but as a support for domain knowledge. So that's the claim that I'll make. In fact, I used to have a somewhat more dangerous title for this talk, but I was not sure whether the RRI would lose its funding because of such a title. The title was actually Data Science and Astrology. Is there a difference? And I'll answer the question at the end of the talk. Yes, yes. So basically the point here is that similar to nuclear science or technology, data science is certainly can be extremely powerful and a potent way of addressing problems, but at the same time it should be used with not just care, but great care. Okay, so if we just step back and look at the evolution of science, the popular wisdom is that it has gone through these four stages, so there's four stages of evolution, starting with originally where you just had empirical observations, looking at data, looking at especially natural phenomena. This was particularly true in the world of astronomy or in the world of chemistry. So you look at chemical reactions. Then we graduated to this world of theory where we were trying to explain the data. And one of the most famous examples is, of course, our Newton's gravitational law. And there are many other such laws which describe how nature behaves. Subsequently, we moved on with the advent of computing into the world of simulation, where you are actually creating the data by first creating models and then feeding various kinds of input parameters, and these were generating the outputs. So fluid dynamics is an excellent example here because it's very hard to actually build these tools and to try them out in the real world because there are potentially catastrophic consequences if you got them wrong. So you would like to simulate the behavior and check what the various features of this particular phenomena that you were trying to model within your simulation. And then, of course, today, where we say that data is the new oil and rules the roost, we have the information age where essentially data has become the genesis of science itself. Okay? And we see this again in astronomy with black hole identification from space images. And what is interesting to see that as you go through these 4 stages is that the role of data has moved from being the output now to being the input. And therefore, we run into the potential problem that we may now be putting the cart before the horse. And that's the case that I'll try to make through the rest of the talk. So let's start with definitions. Today, the source of all knowledge is Wikipedia, of course. So the definition is that data science is a multidisciplinary field that uses scientific methods and processes to extract knowledge and insights from a plethora of data, which could either be in the structured format coming from various kinds of databases, or it could be unstructured like what you see in the social media. Now, one of the important questions to ask here is that how is this different from the venerable field of statistics, which has been around for at least a couple of centuries? So if you look at statistics, the primary goal initially was to look at explanation of prior phenomena that you had. Okay? So if you saw various kinds of monsoon behavior, you were trying to explain why you had deficient monsoons in some years and you had surplus monsoons in other years and so on. But it was largely being done manually because the resources were not there and they were only dealing with limited data because that's all the amount of information that they could digest. And since they were doing it manually, obviously this was going to be a one-shot exercise. But today in the world of data science, what has changed is that now more than trying to explain the past, you're trying to predict the future, saying how will the next monsoon look like as opposed to what had happened in the past. And because we also now have this huge computational resources, plus the data sensors which can feed these models, we can now have automated and iterative techniques that do many passes over this big data. But if you look at the heart of it, it is still statistics. And it's actually, you can think of it as statistics on steroids. And there is a kind of a nice cartoon on this on the web that you'll find, where you say that you start with statistics, but when you put in all these cosmetic effects, eventually it becomes AI. So you start with statistics. When you're implementing, you call it logistic regression. Sounds more impressive. When you are hiring for your company, you call it machine learning. Okay, nowadays it'll also be said as deep learning, reinforcement learning. And then when you're fundraising from the VCs, you call it AI. That's it. But the heart is still the same. Nothing has changed. And here is another cartoon that you'll see about data science, the craze for it. Who wants to become a data scientist? Everybody raises one hand or maybe both of them, right? Who wants to learn programming? I don't know how to do it. Okay, it's a boring stuff. Who wants to learn statistics? Okay, despite the previous talk, they say, I don't want to know combinatorics. I don't want to know statistics. Let me just do data science. Without realizing that only if you know this, can you do this. Okay, that's the problem. Now, we in India especially like to think that all great advances in science came from our ancestors. But for the large part, this is just wishful thinking. But surprisingly enough, in the world of data science, we can legitimately claim some credit. And this is because of a notion of what was called as computational positivism. And if you want to read more about it, there is a very nice exposition of this idea by the late Professor Rudam Narasimha, who, of course, as you would all know, was the doyen of our aerospace industry. And he had this very nice article in the Economics and Political Weekly. This was about 20 years ago, which said that let me compare axiomatism and computational positivism. And these are two different mathematical techniques which were being applied to the exact or the hard sciences. So the difference is that if you looked at the earlier Hellenic approach or the Greek approach, they were always trying to start with various kinds of axioms and build up the entire superstructure, saying, why do things happen? The Indians were much more practical, saying, how do we care why it happens? Can we characterize the behavior? So we don't understand the behavior, but we can characterize the behavior. And this is what they call as making the computation match with observation. So you don't understand the gravitational law. You're not able to bring that up, but you're able to do the computations to tell you what the effects are. So this is called as Drig Ganita Ekya, which in Sanskrit means that you're trying to match computation with observation. So here there are no models, there are no deductions, they're just formulas, okay? Theories and so on. So this is very different to the Hellenic approach. So you can actually think of this as Aryabhatta versus Ptolemy. Okay? Okay, so just to give it its due, so that you don't think I'm a completely biased observer, I'll tell you a few good things about data science, but the rest of the talk will be a rant about how it's actually mostly bogus. Okay? So many of the, especially the oil companies, and if you're familiar with the way that oil plants run, you know that it is an extremely difficult operation to start an oil processing plant and to shut it down. It actually takes weeks because there is a very huge chemical plant. Many of the pipes and the processes there have to be shut down in a very systematic manner. Okay, you cannot just say that control or delete and reboot the system. It's a very painful process. Therefore, if they have to shut down the plant or restart it, it's an extremely expensive and time-consuming exercise. So what the oil companies would like to do is to be able to predict when failures are likely to occur for various components so that they can preemptively go and replace those parts. So Shell has actually built this analytics platform, and one of the large Shell research groups is actually here in Bangalore right now, close to the airport. They run predictive models to anticipate when any of these parts, which are in the thousands, might fail. And because of doing a good job on this, their inventory analysis now has become, the inventory has become substantially reduced, because earlier you never knew when something might go wrong. So you keep a large amount of spare parts in advance. But then you are going to be wasting the storage space, as well as the fact that some of these components that you have may actually die because of the fact that they have been around for a long time. So instead of days, now you can bring it down to hours. Okay? So it's something like just in time you can do it. And this has reduced millions of dollars on their cost of inventory management. The same is true even for transportation. Okay? So many of these, and you would already be familiar with the kind of, when you are ordering cabs nowadays, everything is going to be dynamic. There is surge pricing and so on when you go with Uber or Ola and so on. Okay? So if even in the communications world, they want to find optimum shipping rates. And things that contribute to it depend on the weather. Of course, if the weather is bad, then you're going to raise the price and so on the terrain and the drivers that you have. But now they're able to predict these freight rates correctly days in advance with high accuracy.
Is it because they are the largest company and they can manipulate the prices?
No, this is not the case of the usual thing where you have an oligarchy which is trying to change the values. They are actually able to do a fairly good modeling of the entire exercise, because there is certainly a lot of competition in this field. So if you look at our courier services and so on, there is a very large group which can do this, right? Yeah. But actually that could also be a good answer to why this is there. And then of course coming to health, which is the concern for all of us, is that in medical imaging, data science has proved extremely useful, because if you look at all these existing techniques, like the MRIs or the CT scans and so on, they give you very good visualizations of the inner parts of the body that are not normally seen from the outside. And traditionally what has happened is that doctors have been looking manually at these images. I'm sure any of you have gone to doctors, you just put it up to this screen, put a light behind it and look at it and say, okay, I'm going to charge you 3 lakhs. Okay, we'll remove some of your parts and then we'll send you back home, right? So they manually inspect the images, which then means that it's often that you miss certain features that are there. Okay? Because these are microscopic deformities that are hard to see with the naked eye. But recently what people have done is, and some of this work has also been done at the Indian Institute of Science, is that you can use these deep learning technologies to be able to find out, using techniques like image segmentation, to find all these deformities which should be flagged and are potential harbingers of diseases that you might be suffering from. So all this is the good stuff. But then let's look at especially what has happened in India with regard to data science. We like everything very quickly, okay? Right from Maggi noodles to IPL and so on. It should be quick, right away. So they say, I can make you a data scientist very quickly. No problem at all. There are data science boot camps which say, just come for 3 months, and that too not, don't leave your regular day job. Just come on weekends. Okay? If you have the time, come on weekends. What are the outcomes? You will be a master, master of all 3 elements of data science. You're a master of statistics, you're a master of all the software programming tools, and you have business knowledge. Okay? Just 3 months, weekends. And then they say, we will, as a bonus, we'll also give you guidance on how to craft your CV, okay? Which will reflect all this mastery in these 3 different fields here. But in fact, we are today greedy. Say 3 months is too much. I don't have time for that. No problem. Here is another advertisement that you would see on the back of the auto rickshaws here in the newspapers. I'm not making this up. This is all true. Data science. Become a data scientist in 1 day. And 1 day is also a problem. I don't want to miss my lunch. Only 10 hours. Watch Netflix and Amazon Prime the rest of the time. You're okay. So this is a Cinderella-like change. That go in here, come out the other side. You're a data scientist. McKinsey survey was done on what are the skill sets required for data science. We all love these surveys because they get a lot of data and you come out with some predictions based on this or analysis. And he says that data science is now being integrated with industries across all sectors. Okay, music to our ears. So we are expected to have a broad set of skills. And what are the skills? You should know Python. 44% of the guys who do data science or claim to do data science use it. You should know Tableau, the software development environment, and RStudio, because 51% of data scientists use it. And you should have an in-depth knowledge of the Hadoop platform and the file systems here. What is interesting here is that these are all programming related skills. Not one word is mentioned about where the science is coming in here. Yeah, no.
And I think you are just critical of the business model. And nothing to do with that.
Yeah. Well, I'll come to the science part, and I have a chemistry example for you specifically. So just wait for that. Yes, I'll brought that. But just wanted to point out that how in the popular imagination, data science has been reduced to programming. There is not one word of either mathematics, let alone combinatorics, or of saying that I should understand domain well. He just says that learn the programming tools, and now you're licensed to drive. Okay, so here is the myth. Data is the new oil. Everybody loves this. But I call it actually that is the snake oil. Now we say data science is the new quantum mechanics because we love Richard Feynman and we say that this makes it look even more impressive. But if you look at what Feynman said, he said that the people who say that they understand quantum mechanics actually don't understand it. Okay, there's a famous statement from him. And then my own thing is that if you have been watching Raymond D'Souza, ABCD, anybody can dance. Anybody can do data science today. Okay? It doesn't matter. Remember, only 10 hours that it takes. So what is the reality? And this is the most important thing to remember. The key word in data science, although the word data comes first, is not data. It is science. Okay? We should not forget that. This is in capital letters. The other one is in small font. And if you do data science right, then it actually requires a deep understanding of the underlying principles. So you need to know all the physics and the mathematics and the biology and the chemistry and the data domain, not just programming environments. And this was put very nicely by Ronald Coase, who was the Nobel Prize winner in economics in 1991. He said, if you torture the data long enough by doing all kinds of operations on it, okay, make various kinds of transforms on it, put a fast Fourier transform here, put in a Laplace one there, do a Lorentzian polynomial on this side, do something to it, it'll finally confess to anything that you want. Okay? So this is the problem. Okay, now let me give you actually some real world examples, and several of them will come from not the business world, but from scientists who should have known better. Okay? So there is a very nice article in the New York Times in the op-ed section. This is again about 10 years ago. So this was by Professors Marcus and Davis, who are part of New York University, very well respected place. And this has a kind of a sarcastic title. It says 8, oh no, it's actually 9 problems with big data. And what they said is that big data is prone to giving scientific sounding solutions. So you'll give things to the nth decimal place and you say, this is the variance, that's the standard deviation, here is the various kinds of percentiles, the box plot, all of this, to hopelessly imprecise questions. So the danger with data science is that you will get answers, but you have asked the wrong questions. What we always say in research is that more than the answers, it's important to ask the right questions. It's important to ask the Mason's conjecture. But now what we are doing is that because we just have the data, we cannot resist the temptation to ask ridiculous questions. So let me prove that again by example. There is a study, and again not done by the Yeshwanthpur Academy of Sciences, but by MIT and Google. And the study they did was to say that who is bigger. All of us love rankings today, unfortunately, because they mostly are meaningless. But they say who's bigger. That is, I want to rank the historical figures according to their impact on the world. Not surprisingly, Jesus Christ comes first. But then Hitler ranks higher than Aristotle. And you would expect that Aristotle would be turning in his grave with fairly high angular velocity, given this insult to his contributions. The only reason this is happening is that there are more web pages about Hitler, thanks to the Proud Boys and other people like that, than Aristotle. But if you look at the impact, nobody would put them even in the same league. Okay? But the book brought this out. And again, the problem here is not the data. The problem is you ask the wrong question. You cannot rank historical figures across centuries. Just like we cannot compare books across centuries, you cannot do this. So you are asking the wrong thing in the first point. And therefore, we need to ensure big data does not become huge nonsense. Now, here is a very interesting approach to this problem. In 2017, there is a course at the University of Washington, Seattle, which is again a very well-respected university. There's a course by Professor Bergstrom and West, and this is a real course. I'm not making this up. The title of the course itself is Calling Bullshit.org. That's the name of the course. And somehow it went through the university administrators. I'm sure it would not have happened in our institutions, but they were actually able to do this. And it's a 3-credit course. You actually get credit for it. And it says, how do you call bullshit in the age of big data? And the preface here is very interesting. He says that we will look at the fact that highbrow nonsense used to come couched in big words and fancy rhetoric. But today, we see it presented in the guise of big data and fancy algorithms. So the problem still remains, except that the manifestation has changed. And the entire course is focused on looking at how do you identify and, in a sense, flag these kinds of errors. So I'll show you a few examples from that course. First is a trivial example which Professor Das would say, okay, this is coming from the advertising world, don't trust too much in it, but it's still interesting. Nestle says I'm 99.9% caffeine free. Say, oh wow, this is great. Okay, then even if I drink it, it's not going to affect my health. Until you realize that pretty much all coffee is 99.9% caffeine free, including the one in Starbucks. Because at least there are not too many students here, so maybe the teachers will be aware, but students would certainly know that caffeine is a very potent drug even in small quantities. So this is just saying the obvious. It's not giving anything new, but you feel good saying that I'm drinking healthy stuff. Okay, so let's go from the business world to something, to a paper that actually appeared in Nature. And Nature, as you know, is pretty much the acme of all scientific journals in the world. Everybody would kill to get a paper in Nature. Okay? So this is a paper in Nature 2004 by Tatum et al. And they say that they look at a very interesting question. They say that let's look at data, and this is looking at sports, and looking at the 100-meter dash in the Olympics. And you want to look at the gold medal time, that is the sprinter who has the fastest time, for both men and women over the last about 120 years that we have had the Olympics. So this is the graph that you have. Starts with 1896 when the modern Olympics started, comes all the way up to here. So this when the study was done in 2004, so it kind of ends here. All the blue points that you see are with regard to the men. So you can see that it started around 11 seconds, and now it has come to, thanks to Usain Bolt and others, somewhere around the 9+ mark here. Right? And then if you look at women, you see that it started around 12.5 and has come down to something of the order of 11. So this looks very good here. This data has been plotted. Now the question that they want to ask is that when will women beat men? And the motivation for doing this is to say that look at the slope of this. Okay? We already heard about concave down and so on, all this derivatives. Look at the slope of this. They're going to intersect because this has a sharper slope than one here. When will they intersect? 2156. So in 2156, I'm sure all the women here will be happy. Women will definitely beat men for the first time. What is the advantage of giving a prediction like this? None of us will be around to see it. Okay? So you can gladly make these predictions. Okay? But you can see the ludicrousness of this by extending the idea a little more and saying that, hey, I'm so good at drawing these lines. Can I go till here and touch the x-axis? When will I touch the x-axis? Just another 500 years. In 2636, you will get less than 0 seconds. You will finish the race before you started it. Okay? Here is the problem is that you are extrapolating, and there are statistical terms for this kind of bogus extrapolation, where you assume that whatever linearity you saw here will continue indefinitely. But we know with body physiologies that all of this essentially will have a decaying exponential kind of a behavior here. And this is what you will see as well here. But it's too tempting to just say, let's continue this graph and see where they do it. Okay? None of this is true. And again, this came in Nature. Okay? Now I can see Professor Das is a little more worried. Earlier he thought he could blame it only on the business people. Now it's the scientists. Okay. Let me give you another one which came from scientists. And this is something that I absolutely love. Okay? This is a study done from the University of Sydney, again very well recognized, by Professor Kenny. And the title of the article is Music to Die For, and it's meant literally. They're looking at when musicians die. I don't know why they asked that question. Again, as I said, with big data, you are encouraged to ask the wrong questions. They want to know when musicians die. Okay? And what they want to do is to say that, does it depend on the kind of music that you are doing? Okay? So here on the x-axis, what you have is the different genres of music. Of course, this is all Western music, so you have blues, jazz, and so on, all the way to rap and hip-hop. Okay? So in our world, we could have done bhajans, devarnamas, and so on, and all the mashups and the Bollywood music, as well as Bhangra, all of this stuff could be put here. And they looked at y-axis is the age of death, the average age of death of musicians who are in that particular school of performance. So what they have done is, for women, this is the average US life expectancy, and the blue is for men. So this is the average population, and these are the musicians. And you can see that the musicians who are playing the kind of the classical kinds of music, like the blues and jazz and so on, they all tend to live to ripe old to ripe old ages. But look at all these fellows here, okay, who are all in these things like punk, metal, rap, hip hop. They die early. So if you are in this school of music, not only do you die early, the subtext is here is you deserve to die early. Why? Because they're associated with licentious or bohemian lifestyles. So this proves it, saying that, look, I know you guys used to have all these drug-infested parties. Now look at what you're suffering, and this is what you deserve to have. Whereas if you're singing bhajans and so on, and devarnamas, you will live to a ripe old age. And if you actually see Carnatic music, you'll see many of the major musicians there all lived very long. Okay? Shamangundi Srinivasa being a particular example, who lived almost close to 100. Yeah. So, but what is interesting here now, all this proves what was your internal biases. It actually even came out in the Washington Post saying, this is worse than war. We don't lose half our army in a battle, okay? Because now people are dying at half the age. But the thing is, there is a simple statistical mistake that has been made here. When you look at the average age of death, these are all the new age music schools. These all have been there for a long time. So the people you are measuring here is not a representative population. It's only those who have died in the last 10 years, but that field of music has only been there for the last 20 years. So you're looking at the people who die early here, but you don't have a handle on the people who may be living long. Whereas here you have a much larger time window in which you could observe this data, and therefore you could have much better statistical properties. Okay? So because there are new schools of thought, or also schools of music, the data does not showcase the long-term behavior, but only the temporal behavior over the last few years, and that is showing you in a sense, a biased view of the underlying information, because you're not looking at the people who are actually living longer. Because this is focusing, as I said, for some morbid reason, only on the people who died. Now, in the media, it's converted from average age of death to life expectancy, saying, you do rap music, you die early, you deserve to die early. Okay? That's the equation. Okay. So, in the statistical world, basic problem here is that, which we all tend to make, is you mistake correlation versus causality. And you're missing the intermediate variables that need to be used to connect up this information. Okay, now let's look at some other such cases. US airline rankings. Okay, everybody loves rankings again. Okay, all our administrators and directors all the time are looking at the ticker tape, saying, "What's my ranking in the NIRF or in THE or something like that?" 2020, okay, the very best airlines was American Airlines, and the very worst was Allegiant Airlines, which is a West Coast US West Coast airline. In 2019, now suddenly in 2020, there's a complete phase shift. The top guy goes bottom and the bottom becomes top. Okay? Allegiant becomes number one, American becomes worst. And you're saying, my God, what happened? Okay? And they said that maybe Allegiant has done something phenomenally well this year compared to what they were. They learned from the mistakes and did it. It's not that. It's just that they changed the parameters in the ranking. The parameters that were changed was that earlier, the safety parameter for baggage, saying that they did not lose it, was number of lost baggages by the total number that they carried. Okay, this is the new one in 2020. Previously, they were looking at number of losses by number of carried passengers. They have just changed this parameter. Now, why this small change here, which looks on the surface to be a superficial and a trivial change, actually had this impact is that Allegiant is a low-cost airlines, where they actually charge you more for the baggage than for your own transport. The moment you bring a bag, they essentially charge you the entire plane. So everybody who travels on that comes in only with hand luggage, because you cannot afford the check-in baggage. So there is nothing to lose because there is no baggage. I didn't lose 0 bags. That's it. Okay? And therefore you find this to be the case, and suddenly Allegiant looks good. Okay? And the same is again true, I would say the risk of upsetting people here is that most of our academic rankings of universities, either in India or internationally, is all nonsense. They are not worth the paper they're written on. Okay? If you just look at the details, you'll see that they are all manufactured numbers because we all crave rankings. But it is the wrong question to be again asking. You cannot measure education. Education is a self-transformative process. You should not lower it down to saying it's a 100-meter sprint. If you take a student from a small village and transform them into doing combinatorial mathematics, how do you count for that as somebody coming from an IIT and doing the same thing? The transformation is huge in one case and minimal in the other. But we are not looking at any of that. So please do not reduce education, and since all of you are teachers, to rankings. They are actually nonsense. Okay? And the reason I say this with so much emphasis and passion is that we see that every day we are being dictated to by the mandarins in Delhi about saying, what's your ranking? Okay? To me, it sounds like the movie Priyanka Chopra saying, what's your Rashi? Okay? You have to look at what is the transformation you're achieving in your students. What is the learning process? Not magical numbers and saying, okay, you're 25 or 23 and so on. In fact, a few years back, the rankings were flipped between IISc and IIT Madras. And there was consternation saying, oh, how come we changed? And I told them, both the numbers are wrong. It's not that either of them are correct because these are both huge elephants. Elephants do not change overnight. They're exactly the same. They are in the same equivalence class. Okay, those numbers come with large error bars. There's large variance around them. Don't take them seriously. Oh, yes. I'll get back to that at the end of the talk. Yeah, I'll tell you. Yeah, so as I said, these passengers don't want to check in bags because otherwise it's more expensive than the seat itself. Okay? So this is one. Yeah. Now coming to things that which you might be interested in, this is the NIH, this is the National Institutes of Health, equivalent to our DBT in India, which is how to do grant allocations. And in 2017, a new administrator came in. Every new administrator wants to put the stamp on it saying that I did this. So what they said is, let's look at the return on investment. So on the x-axis is the amount of grants that is getting, the person is getting, and the y-axis is in some sense the return on the research measured by citations or some other factor like that. So what is not surprising is again we got our favorite concave curve here, that as you give more and more grants, you're going to be having less and less returns on this. So decreasing returns on more grants to single investigator, and then there's a natural understanding of this. Of course, we know why this is happening. If I give you 4 projects instead of 1 project, your time is divided between the 4 projects. Naturally, you pay less attention to them. So therefore, the research outcome is going to be poorer. It appeals to our senses beautifully. And it says, what is the proof? Look at the concavity of the ROI graph. But it's very nice that we had the previous talk, because these are both on the log axis here on both x and y. And log concavity does not imply linear concavity. But any curve you look like this is extremely attractive. And these composite results do not predict the individual behavior. Okay, now let me come to the example that I was waiting for Professor Das, because he might have said that that's all other people doing it. Chemists are supreme. Okay, that's what we believe in India, at least, or in IISc. This cannot happen in the world of chemistry, right? Yeah, so here's a very interesting thing. Predicting reaction performance in carbon-nitrogen cross-coupling using machine learning. Okay? Everybody loves machine learning today. Okay? That's, we are supposed to do it. And this comes from, of course, one of the most well-known universities, Princeton University, and it came in Science, which with Nature is again the top journal in the world. Okay? So this is, as I said, not in the Yeshwanthpur Academy of Sciences, but in Science, and by very well-known people. And they said, let's look at the impact of isoxazole additives on how reactions are poisoned during Buchwald-Hartwig coupling, which is apparently a popular technique in pharmaceutical synthesis. And they said, we used an advanced machine learning technique called decision forest, where you have a large number of classifiers and you take essentially the group-wise interpretation of them. And says, worked much better than simple linear regression. Yeah, we used sophisticated techniques, got good results, successfully applied this even when you had small amount of input data, and was able to do good generalization to future cases. This looks like a poster child for machine learning in the sciences. Okay? This is April 2018. Everybody loves this paper. 6 months later, same journal, Science. Now, from the other end of the other coast of the US, University of California, San Francisco. There's a comment by Chuang and Kaiser. And what they said is, if we replaced all these carefully calibrated values given by the previous paper related to the resonance shifts and the dipole moments and so on of all of this, we just put random values, okay, throw junk at it. It will produce a model that had similar performance to the Princeton outcomes, which basically means that there was an inherent structure that was there, which was already present. So no matter what junk you throw at it, that is always going to surface. Okay? So the importance of these high additive features cannot be distinguished from the hidden structure within the data set. Now coming closer home, if you said, oh, right now all the examples he gave was outside of India. Okay, all those guys don't know how to do data science. We do it in 10 hours, we are great data scientists. We know how to do it well. Look at COVID. The Sutra model, which was the government officially certified model, which came in with very well-known people, especially in the control theory and computer science and so on. But there's a very nice article in the Hindu about how the entire second wave was missed by all our models, and in particular, this so-called certified model, which was considered to be super model. Okay? So if you read through the Hindu article, which is very nicely done, they say the Sutra used a data-centric approach. Everybody should sit up and clap and say, yeah, data, this is the good stuff to have. But then it says that the equation that gave out estimates needed certain constants. Okay, this is like saying that in India, we know that if your scooter doesn't start, what do? You bend the scooter to the left. And then magically it starts. Nobody knows why it happens, but bending the scooter works. Okay? Maybe there's a gravitational pull of the petrol or whatever, something. So it requires certain constants. Okay? These numbers kept changing, and their values relied on certain input data and the reliability of it. And the equation couldn't figure this out. And so a rapid acceleration of cases couldn't be predicted in advance. And in fact, this problem is not there just for this model. We had at least a dozen models in the entire country. Everybody who was anybody said, I have a COVID model. Okay? And what was interesting about them is that all of them were wrong. Okay? And this is the same thing that you see in the exit polling for elections also nowadays. Okay? pretty much everybody gets it wrong. That's the only commonality across all. The other issue here was that Sutra model is problematic because you have too many parameters. Okay. When you throw in a very large number of this, you really don't have a handle on what is the science occurring underneath. Because you need to know the major things that actually influence the behavior. Not just randomly say that I will take the length of the road or the weather also into account. Okay. You need to be careful in what you model, and therefore you have a danger of overfitting to a particular set of data. And this is the most important thing. Although I am from the computer science world itself, I keep saying that we should not have the arrogance that just because you have a computational tool and you have the data, that you can replace the domain expert. That's actually what happened here. They did not have epidemiologists. They had excellent computer scientists, they had excellent resources, they had excellent mathematicians. But they don't know how actually diseases travel on the ground, for which you actually require people who have seen grassroots health behavior, especially in a country like India, which is very different from other places. So therefore, this is the critical part, is domain expertise. Yeah.
In countries which have good epidemiologists, they are not doing work.
So data science doesn't work. Yeah. Yeah.
So it's not that the epidemiologists who could actually have many of these models don't predict it. That's where the problem is.
But see, the government is putting the trust in these models. That is the dangerous part, because we now say, oh, this is the certified model, we're going to use this to make public policy. Or you recognize that, as you're saying, that it's a hard problem, don't even think about it. But we like to assign a certainty to things which are inherently stochastic, okay, or non deterministic.
It's possible that the government is passing the buck to the city.
They passed COVID. I don't know what the buck, but certainly COVID was that. Yeah. Yeah, I'll just be done here. So, okay, but those were comparatively things saying, okay, even if you made mistakes with regard to the music or with regard to the Olympic scores and all, it really doesn't change anybody's life. But actually, there is a very nice book called Weapons of Not Mass Destruction but Math Destruction. This is by Kathy O'Neill, who was a Wall Street Journal reporter. This was in 2016, where it actually says that how data science can be dangerous, not just incorrect, but can actually be dangerous because it increases inequality and actually threatens democracy. Okay? Because nowadays our lives increasingly depend on ability to make our case to machines. Whatever you do, OTP, okay, you get sick and tired of saying OTP, every small thing they ask you for that. Without that, you cannot move forward, right? What happened here is that they have this Centrelink, which is the Australian organization, which basically ensures that people who are under the poverty line do get some support from the government system. And what they did was that they had an automated compliance system, and they looked at the income that was self-reported by clients. Now, many of these clients are people who have seasonal labor, okay, who might be doing in the summer because they're picking fruits or vegetables and so on. But what the system did was saying that whatever you got in the summer, I'll extrapolate it to the entire year. Okay. And then because of this, now suddenly they said, you guys don't deserve it. You are actually doing well. You are close to Nirav Modi and Malia now. Okay. You just multiplied into 12. But actually their only income was only in the summer and nowhere else. So if, for example, if you are manufacturing shorts, you can only sell it in the summer. The rest of the year you have to be sitting around, right? So, but then you have all these extrapolations that are being made, unfairly penalized many people who deserve these benefits. Okay? So now we have the Bhagya scheme even in Karnataka. You have to actually look at these kinds of aspects, saying that how do you define poverty lines? What is the kind of time window you're looking at? It's easy to say that, but when you actually put it inside a tool and you have to make your case to a tool, it's very hard to argue with it. Okay? This especially happens with banks, is that if you go to a bank and they say no, nowadays all our banks are interlinked, there will be a record somewhere saying that we said no to this person for getting a loan. When you go to the next bank, that black mark is already there. So it reinforces their presumption that you are not a good risk factor, and therefore I will also deny you the loan. Now you go to the third bank and say, hey, two banks already said you don't deserve a loan, I will also say the same thing. So there is a domino effect here, and in the end, you keep getting denied a loan. The only bank that cannot deny you a loan is Yes Bank, because they have put in the title it's yes, so they cannot do a loan. But as you know, Yes Bank itself got into various kinds of trouble. Okay? But this is the problem that you will have, because you have a track record now and everybody will continue on that historical trend. Same thing is happening with predictive policing, which you already see now in France, the kind of trouble they've gotten into. Based on demographics, you can alienate innocent targets, where if I keep saying that you are guilty, whether you did it or not, you say, I might as well do it. Because no matter what I do, you're going to say the same thing. It's probably better to just go and actually do the crime rather than just be unfairly accused of it. And you'll also see this in many of the companies nowadays. People are being treated like machine parts. Okay? So I think you saw that with Twitter saying that if you're on the way to the office, don't come. Just go back home. Okay? You'll be fired anyways. Okay? Okay. And then, of course, this is a extremely pernicious and dangerous problem in a country like India, where you can have directed behavior, where you modulate the news feed in order to selectively push a certain kind of opinion or pander to a particular segment of society. And we see this daily with fake news. Most of your WhatsApp is filled with images that are fake news, right? Okay, so here's the conclusion. Data science, yes, can be useful, but important. Use it as a tool of last resort. After you have understood everything else, and then say, this is the hypothesis I have, let me try to validate it by using this data. Don't use it as the first thing, saying, I have the PyTorch and my Python programming environments, I have data, something good will come out of it, let me just let it loose on it. Again, remember, tool is a support and not a substitute for domain expertise. The computer scientists cannot replace, however much they like, the physicists, the chemists, and the biologists. Okay? You have to give respect to the domain first and then say that we can be a supporting role here, but you cannot be the main actor or actress here. You can be at best supporting actor. And finally, the tool output should be compliant with science and not inherent biases, however tempting they may be, like as you saw with the music case or the other cases. You rush to associate because you already are inherently thinking that, and if the data validates it according to the flawed model you build, you say, wow, this is wonderful. The data confirms what I always thought. Okay, so as I said before, data science has enormous potential, but it can be equally destructive. It's important for us to make sure that we don't end up in ruining society. And you remember the original question that I had, which I did not have the courage to put up here, which is data science and astrology. Is there a difference? So at the end, let me say that yes, there is a big difference. Astrology is more accurate than data science. Right? Okay, thank you.
Okay, so I have this intro question chart. Okay, let me first have a disclaimer that I don't believe any predictions of any statistics. It doesn't matter how much the hard work going to actually come up with that kind of number. Because I only believe that statistics is cool, okay, for a prognosis of doctor diagnosis. It doesn't have zero predictive power. But is there anything that is proven that is not true? Is there a fundamental proof that, okay, if I see a pattern, that I can predict that pattern will be true? And I don't know, and I have never actually been convinced that there is a fundamental proof. It's a conjecture. You could believe that if it is happening today like this, it will happen 10 years later because under the same conditions it will happen like that. So that's the predictive power. And I believe statistics, no matter how you do it, there is no predictive power, and this assumption itself is actually false, and therefore everything that comes from there is false. Okay, but we can use statistics to actually understand why something won't go wrong. What was actually that was not found before. It's very good for analysis, has zero predictive power.
Right. So that was the traditional view of statistics, saying that let me understand the past as opposed to predicting the future. I would put it slightly in a little more nuanced way, is to say that for especially naturally occurring things, for example, astronomical things and so on, observing patterns usually leads to correct predictions because nature doesn't bother about statistics and says that I'll continue to, for example, do elliptical orbits no matter what you say. It also works when the models are slowly changing and are fairly smooth in behavior. But if you have models where there can be sudden spikes or jumps, okay? Like for example, the first question you should ask is, if you are so good at data science, why don't you predict the stock market and become better than Mukesh Ambani, right? It should be trivial. Okay? You have the computer, you have the data, everything is easily available, bet on the stock and do it. But there you have these sudden delta functions where there are spikes and falls. Once you have a situation where a small delta change in the input can cause a macro delta change in the output, then all bets are off. Because there you cannot really do any kinds of predictions. for example, if you had a model which looked at things that were happening every alternate year, so in every even year you have something and every odd year has something, but you use a model that combined this behavior, then when you do the prediction, you're going to be completely wrong half the time. So it's very important to look at the nature of the progression of the function, whether it's concave or convex, or whether it's log concave and so on, and whether it is smooth or not. Or if it's discontinuous, then certainly all bets are off. And of course, as P.K. Das mentioned, that very often the model was built in a certain environment. That same environment may no longer be true, because in fact, there was a very nice example which I didn't show you here today, which comes from the world of geography and modeling earthquakes and so on. Many of the things have changed in the underlying structures in the interim process. So the model that was done 10 years back may no longer be applicable today. And because much of the environment has changed, like for example, our global temperatures have risen. So whatever model you had built 20 years back, assuming a certain ambient temperature, may no longer work today because all the ambient temperatures have gone up. Right? So that is certainly true. Okay? And but for certain well-behaved things, you could probably come up with reasonable predictions.
Frequently we hear GDP database and criminal violations. Most of the time India is in the part of Pakistan and Sri Lanka is the top. By most of the economies. So what is your, is there any proper data tool or how do you justify?
No, it's also, as I said, it's just like rankings. Don't trust them. Absolutely not. Okay, and in fact, I'm a little disappointed that our academicians have not stood up more strongly against what the bureaucrats have told them is the way to rank things. We should. Yeah. Exactly. See, because, I mean, for example, many of you would be, if they're coming from state universities, you know the difficulties is much harder than in central universities. Where does that get factored into the rankings? Under a lot of duress, you're getting things done. Okay? Where is the credit being given for that? You have achieved transformations which will be much easier in other locations. But we are just saying that what is the square area of your campus, how many international students you have, how many papers you had in science and nature. Those don't convey education, because that is a transformation process. We are just reducing it to numbers because it's very attractive and everybody wants 1, 2, 3. Okay, but as I said, that's like the one which said, who are the most important historical figures? And Hitler is more than Aristotle. So the wrong question is being asked. You should not rank education, because it's inherently unrankable. It's like comparing two musicians. You cannot compare two musicians. You may have likes and dislikes, but there is no way to say that Balamurali Krishna is better than Shaman Gudi Srinivas Iyer or the other way around, right? It's the wrong question to ask. You could do it by putting in certain things of saying that, oh, how many videos did they have, how many likes did they have on the web channels and so on. But those are all subsidiary metrics which really don't convey anything. So my complaint is that because of the proliferation of computers and of data, you are now being encouraged to ask the wrong question, including the one that you mentioned.
Even metrics for scientific journals, life structure or whatever. That's the same, go by fact factor.
Yeah, we have anything on impact factor.
Not specifically about that.
But
Yeah,
not
yeah.
right about.
Yeah, not, but there is an article that was, I can email that to you later, if you can just send me a mail, which was kind of capturing whatever is the information here in a journal article. And of course, it's definitely not going to be popular. Nobody wants to hear these kind of truths, right? Speaking truth to power is not something that is enjoyed by anybody. So, and I come from a department of computational and data science. So my staying in the department itself is, I think, is always suspect when I get thrown out. So it's, yeah, I was just joking about that.
The real problem is that who actually themselves Sutra, and most of the people who are in the Sutra committee were actually very well-known modelists of this country. This country has not produced better than them. Yet, they were not able to go up in the court and say that you should not have questioned the answer. So the actual failure lies there. And when we say the government is telling us, actually it's not the government, it is a set of scientists who the government has entrusted with some job, they are doing this. So therefore, interpretation system is correct. We cannot say the government cannot ask us to do this. Because the government is not actually directly telling you that whatever. I know actually all the people who are actually the government to work actually, Sutra, which failed, and they are not interpreting, but they made a wrong position. He said that there will be no second wave, and even if it is there, it will be lower height in the distribution than the first wave. But then we are very competitive people. I mean, individually, you know some of them actually came belonging to the science, and Giant also knows. So therefore, it's not that. It's just that you need to see that you are not asking the right question and then stand up and say that this I am not going to be able to answer this. It's not no point. It's not worth actually spending time on it. That's where I think.
Yeah,
that's
no, exactly as what he said. The credentials of the people who are part of that, so there's no criticism of them personally, they are impeccable. They are the who's who of Indian science. They did it with good faith, but the problem is, the systemic problem, as you're mentioning, is that you are getting sucked into something which is actually the incorrect questions that are being asked. Then nothing can save you. Okay.
So that's what actually, if you remember that Raj talk, that you have to actually ask a precise question. If you cannot ask a precise question, you don't have any answer. I mean, you may actually gain from the answer that you get, but that's hardly the consequence. Doesn't matter. So therefore, there are all these things. Anyway, if you have any more questions, please shoot to Mr. Because we are doing many things in history, so I get this chance to talk to you. But you probably haven't seen it, so.
So in the first slide, you shared a definition about data science as a multidisciplinary, as per Wikipedia. What's your take on that?
Yeah, certainly that is true, is that you have domains, then you have computational tools, and then you have mathematical foundations. So all of this has to come together. Now, it's not necessary that the same person does all three of them. So this is where sometimes the arrogance comes in, is that I know best. Okay. If you can say that, look, we have people who are experts in each of these, and I would still say that the first among equals should still be the domain scientist. And then we are all the supporting cast. There is a person who knows the computational tools well, somebody knows mathematical foundations well, all that is great. But we should recognize that we are not center stage. That should rightfully be given to the domain scientist, who can see when we are making actually horrendous mistakes. Just to give you a very simple example, all our computer scientists students today, anything you ask them to write some output data from any kind of computations that they're doing, they usually give it to 25 decimal places. And I keep telling them, how do you get 25 decimal places when the original measuring instrument itself did not have that kind of precision? We know in physics 101 that you cannot have more precise results than the original fine grained accuracy that you had in the original machine. Okay? If your voltmeter can only do in volts, you cannot produce millivolts at the other end of it. But when you ask them, they say, sir, computer gave that answer. I have cut and pasted. So we fall into the danger of cut and pasting because we don't understand physics. And therefore, that is where there should be this cautionary people in the domain who say that, okay, despite all the other saying from your data, this is wrong. It violates some law of Newton's physics, maybe some the fourth or fifth law, which we don't know about, but there is a violation. And that gut feeling is very important. Well, otherwise, we will trust whatever comes out from it. Like as I said in the Allegiant case, if you had asked the airlines people, they would have said this is nonsense. But we just looked at the data and said, oh, this is, I mean, everybody loves this transformation story, right? Saying that somebody has come from the bottom and they reached the top and the top guy went to the bottom. So this cyclical trend is something that we would all enjoy. And it serves them right. Yeah, right, right, right. Thanks very much.